and modern physics. And then the last one, which will be meant for you guys, will be the biological effects of radiation. That's what are some of the causes of radiation in our system. So that's all what we'll be doing for today. So starting off, so starting off, we start with the nuclear reactions for session 1. Sorry, is Mr. Castro is not in yet, right?
Yes, sir.
Yes, sir.
Okay, so is Madam Felicia too. Mr. Ibrahim too is absent. Oh, I see. Anyways, so nuclear reaction in general talks about the type of reactions that occurs when we have an atom, right? What are some of the reactions they undergo through, or what are some of the properties or characteristics they show when they are in reactions? That's what they talk about in the whole nature. And basically, as we said, for every atom, for it to be stable, the number of protons and the number of neutrons have to be the same. In the case where there is instability, means the proportion of the protons to the neutrons are not the same in the nucleus. And that brings about what? Radioactivity. Because we said when they are not the same, it intends try to lose some of their energies, their protons or their neutrons, so that the number of protons and neutrons will be the same. In the case of releasing some of these things, they are undergoing radioactivity. Yes, we mentioned that as well. And in some cases, not always like that. Sometimes we just try to separate either two or more one nucleus to two or more daughter nuclei, or we have more nucleus and want to combine it as one. In each case, energy is being released. Okay. So, for example, if you have initial product, let's say X, right, and it's a parent nucleus, and we want to get a daughter product from it, or it's unstable, so we want it to be more stable. We can sometimes hit it with either a helium atom, either a neutron or whatever. So whenever you hit it with it, it then intends to separate itself into two, where we have the daughter nucleus and also the particles that are being emitted. And these particles can either be a beta positive, in that case we call it a positron reaction, or yes, positron reaction, or when it's negative, that's where you have the negatron. And when we have the atom being captured here with electron, that's where you have the electron capture. In some cases, we can also have alpha decay or alpha reactions, where I don't know, do you have this and an alpha particle or a helium atom, or we can have the gamma radiation, where after this we have the daughter nuclei and also an energy being released in the form of gamma radiation, so gamma rays. Okay, so that's the whole thing that the nuclear reaction is about. So, for example, as we all know, for the reaction, there's a shorthand, right? This one I know you know. It shouldn't be something you have to tell me you don't understand. And that's what we have here. So that the S is the parent nuclei and the A is the the atom you are using to hit the parent nuclei for it to separate. And at the end of the day, you have the daughter nuclei and the emitted particle. Likewise, the same way over here. So with this one, have an intermediate state, which is the I. And this I is what is in turn separating to give us the Y and the daughter nuclei. But in our cases, we don't really care about the intermediate section or the intermediate part of the reaction. Our interest is always between the parent nuclei and the daughter and the emitted energy that we are looking for. And that's all what our interest is. And as we also treated that in case of any nuclear reaction, you have to make sure that conservation of charges is conserved, conservation of number of neutrons is observed, that the number of protons to the number of neutrons is also conserved. And we also talk about conservation of mass. I hope you've not forgotten all this.
Yes.
Okay.
Yes, please.
Okay, so those are the things we also talk about here. So that when you come here, you have to make sure that the conservation of charge is obeyed. Conservation of neutron, number of neutrons is also obeyed. So if you look at this point, we have the mass number to be 9 and 4. And 9 and 4 give us 13. Now, if you come to the product side, we have the daughter having 12 mass number and the neutron having 1. When you add that, it's going to be 13, telling us that the mass number is conserved. Now let's look at the atomic number, so that we have B to be 4 and the helium atom to be 2. When you add it up, you are going to get 6. Where when it comes to the product side, the daughter has 6 and the neutron is having 0 atomic number. And at the end of the day, this is also conserved. So in this case, the conservation of number of neutrons is obeyed. Now, if you look at this here, the charges of the parent side, you realize there are no charges. So it's said to be a neutral atom because there's not many charges here. So at the end of the day, at the left-hand side, you have 0 charge. At the right-hand side, so you can see there are no charges. And it's also having a 0 charge, telling us that at this side, too, the conservation of electric charge is also conserved. Okay, so in the case where we want to also find the conservation of masses, then we will give you the proportion of mass for each of the following nuclide or atoms, so that at the end of the day, you also substitute them in the expression that the mass of this by the mass of this minus mass of this minus mass of this must be equal to 0. And if you get that, then it's also validate that the conservation of mass is also conserved. I hope there is no issue, like everything is
Yes, sir.
okay. So in the case, if you want to write this in the shorthand form, so that you have that of beryllium in the outside bracket, then you have the alpha particle in the bracket, comma, then the neutron, which is the emitted particle, also in the bracket, then you have the carbon outside the bracket, and that's what is being done here. Okay. And as I said, sometimes, yes.
Yeah, when we did it previously, I think it was the alpha particle that was coming first. Because that was what was used to bombard the beryllium. But
Yes.
this is that they are not considering it. Does it mean the order doesn't really matter?
The order doesn't really matter. What matters is always what is before the bracket should be the parent nucleus or the target nucleus. Okay, so what is used to hit it doesn't matter. So in the case, you can either bring the alpha particle first or you can bring it second. It doesn't matter. But if you are writing in the shorthand form, always the parent nucleus or the target nucleus should be outside the bracket. And the daughter nucleus should also be outside the bracket at the right-hand side.
Thank you, sir.
All right. So in some case, yes.
Yeah, so in terms of the X is bracket A, B, and then the Y. In this case, our X is the beryllium, right? The parent.
Yes.
Then the alpha particle is the E,
Yes, the small a.
Then the B is a neutron, right?
Yes, this is the neutron.
And the Y is the C.
Yeah, the carbon.
Okay, thank you.
You are welcome. So as I said, in some cases you can intend eliminating the atomic number and write it in this form. Okay. But then it's always how should I say it? It's always appropriate to write it in this form, showing us the atomic number and the mass number, or the atomic mass and the atomic number, all in the reaction or in the shorthand form, rather than writing it this way. Okay, because for example, assuming in this case, the product you are getting is going to be, let's say, or the byproduct or the method element is going to be, let's say, a positron. That's a positive electron. Okay, and that is beta plus. And if you go and write the beta over here, you see at the end of the day, you have beta minus, you have beta plus. So you are not going to see the exact element that is being emitted. Okay, but in the case where you write both the mass number and the atomic number there, you are going to see, oh, okay, then what you are talking about is the positron. I hope I'm making some sense.
Sir.
Yes.
Then if I with the beta plus, can't if you write the beta plus itself, won't that be sufficient?
It will be sufficient. That is.
Okay.
Is it Mr. Castro talking?
Yes, please. So
I know why he late.
why late? Yeah, why late?
Major 5 marks, I'm Mr. George.
Oh, please, I beg. The mark the NJB.
Waboka.
Someone be fast.
So the question or the issue Mr. Castro raised is also there, that if you are talking about the positron, we always introduce beta positive, right? And the negatron is beta negative. Okay. So if you bring beta positive, we understand that you are talking about the positron. But what's up in the case where you have to also balance the charges, that's the conservation of charges?
Okay.
Yeah, so if you are bringing it there, then at the end of the day, you have to make sure that the conservation of charges is also introduced. But in the case where you just introduce the numbers, that's the atomic mass and the atomic number, you don't have to worry yourself by going to balance the charges as well.
Okay, sir.
Thank you. You're welcome. So for example, they say consider the reaction, the cobalt 59, then bombard with a proton, give you a neutron and a certain daughter nucleus. So how are we going to do this? You know the proton is what? You know the atomic number and the mass number. So you can just substitute it there, then you find the neutron. So when you subtract the neutron from it, then they are going to get the mass number of the daughter nucleus that's being produced. After that, that's where you have to go in there and find the number of protons that is also in the atom. So if you look at it over here, we know when you talk about proton, it's 1, and that's what we have here, right? So if you bombard that one, and you see in the question, it was given P and N, but they introduced the P as a hydrogen 1 atom. It's not compulsory to always write the hydrogen there. You can just write the proton just like the way you are seeing it, and you bring the mass number and the atomic number over there, and it's correct. Okay, likewise, if let's say it's supposed to be a helium atom or an alpha particle, you can just write the alpha particle, then write the charges there. You don't necessarily writing the helium when you are correct. Each other way that you choose to go by it is correct. Okay.
Sir,
Yes.
and I'm on the daughter nucleus. For instance, you use Z and you're able to calculate the mass and atomic number. Are you okay? Or you still have to indicate which element is it?
Oh, it's
Like
not ideally, that's how it's supposed to be. Right? After calculating it, you have to bring the daughter nucleus that is being produced. But we are in a case where I don't want anyone to do chew and pour. So I don't want you to go and choose the that table. I don't want to go and choose so that you know that, oh, okay, 27 is this atom. Okay, so if you just write, let's say X or let's say Y or something, then you put in the mass number and atomic number. I'll just give you your mass.
Please, can you use your marker to write something for us?
On what? What exactly do you want me to? Because I'm just explaining this, and for example, you see here we have this atom, so the reaction is going to be something like this sort. You have a cobalt, right? And you have the mass number to be 59. Okay. And we said we are hitting with a proton, which we know proton is 1 and then 1, right? And that's where the proton is introduced by H. And I said it's not always the case that you have to represent by H. If you don't know that H is 1, 1, you can still represent it by the proton 1, 1, for us to know that that's what is being used as that's what is really need to take the target nucleus. So that at the end of the day, we have, let's say, M. And M is a daughter nucleus that we are being produced. And we don't know the mass number and the atomic number. So let's say we represent the mass number by, let's say, X, and represent the atomic number by Y. So that this plus, now the byproduct or the emitted product is the neutron. So we have our neutron also here. Okay. And that's the exact same thing they've done over here. Okay, so that at the end of the day, if you want to balance the equation or find the number of that's if you want to find the X and Y, if you come here, you have for the left-hand side, okay, we have the hydrogen to be 1. We are dealing with the mass number first. So for the mass number, the left-hand side, we have 1. That's for the hydrogen here, plus 59, which is for the cobalt over here. Okay, and at the end of the day, we are going to get 60. Okay, now let's look at the right-hand side. Okay, if you look at the right-hand side, you have neutron, which is 1, plus, now what is the number of mass, what is the mass number at the daughter nucleus that is being produced? You don't know, and that is equal to 1. As we said, when you are trying to balance this, or in the case of this reaction, always conservation of nucleons is conserved. So that the charges here and the nucleons here must be the same as the ones at the left-hand side. And now since we know that the left-hand side is 60, it means 1 plus 5 must be equal to the 60 that we have at the left-hand side. Please, are you with me?
Yes, sir.
Yes, sir.
I have come. I'm with you.
I'm not you, Cry, the woman who asked about writing something. You, Madam Felicia, you're also late.
Yes, please, sir,
Madam
I'm with
Jemima.
you.
Okay. So that then when you make, okay, so that's at the end, when you make Y the subject, Y will be equal to 60 minus 1. At the end of the day, you are having it to be 59. Okay. Now let's look at the mass number. Okay. Which is, let's say that is a, sorry,
Is it
the
the atomic number or the mass number?
atomic number, sorry. So that the atomic number, the hydrogen is 1 over here, plus the one of the cobalt is 27. Okay. And then we are going to get what? 28. Now let's look at the right-hand side. Now the neutron is 0, plus Now our x we don't know, so plus x,
Alright.
and this must be equal to this the number of the atoms or the atomic number at the left hand side, which is 28.
28. Okay.
So that our x will be equal to what? 28.
28.
So that at the end of the day, you realize the daughter product that you are having over here has the same number of atomic mass, but then a different neutron number or a different atomic number. Okay, because here you have 59 and 27, and here you have 59, but then the number of protons or the atomic number is increased by 1, which is 28. Madam, are you okay?
Yes, please. I am okay, sir. Thank you.
Okay.
Mr.
Yes.
Izzy,
Yes, please.
this is Ibrahim.
I don't know what it. Open so open my attendance.
There is my bow now. Let me follow proceedings.
Hey, we go dinner here, Mr. Ibrahim.
Me de me phone back to join here. Let me say more my bow. Can I phone on network? No. Me say one by na for dinner and police dinner. Not knowing that remember. Later on, I'm finding out from the other point here and knows what I say. Because the whole school got up question. What parents look like now? Sometimes no go how do you say we say because we parent look at me one mass number and atomic mass, but you were not given what do you call atomic number or the proton number. So no, in case it's the same, the question is what? How are you going to detect? Even though you have been given, if there is a way out, you have been given the mass number. How are you going to detect that? Okay, this is atom this or atom that. Because without knowing the atomic, yes, without knowing the atomic number for that particular atom, it will be difficult for you to, deduce the reaction for the reactant and the product side. If you have gotten my question, well, yes, please.
I'm not getting the question well. Are you talking about the fact that they brought the atomic mass, but they didn't bring the atomic number?
Exactly.
That's where I also have some problems sometimes, because if they bring only the mass number and they don't bring the atomic number, I don't know, the only person will say you have to know all the elements on the periodic table, which is also not the best. Okay, so in some cases, at least they should provide you with the table so that it will be so easy for you to do that. But then here lies the case, they won't do that. So maybe, not maybe, if I'm sending the questions to, if I'm being tasked to do that, I'll make sure I provide the periodic table to the question. So that in case if you are giving something like this, and in the periodic table, you have the mass number and the atomic number. So that in the case where you are giving something like this, after solving it, or when you see it in this way, you can just treat and know the cobalt atom or the element of cobalt, and you know the mass number, and you can also trace the atomic number. Then you just substitute in there and solve it.
So Yusuf,
Yes. Yes.
the quizzes. I don't think they are going to give us that table. Definitely for the quizzes.
I will do that because
No, you will give it to us.
okay.
You give it to us, but they will not give it to us because it is because it's online and not on paper, so they won't give it to us. So I'm begging you, if you are supposed to set the quizzes, then I beg for the quizzes here. If you can bring both the mass number and atomic number, that will be okay for us. Just for the quizzes. Just for the quizzes. But with these things, for me, if I'm giving this, I'm not giving the mass number. I think me, I will just use why man was this thing though.
Yes, you can do that, but then how
I'll
will you
just
know the atomic number?
I don't know the atomic number. So I know the method for finding the atomic number, but I don't know the atomic number. So instead of doing that, then I'll just write A for the atomic number. Then I'll just subtract it from.
But that's going to be objective. So if you write that and that is not in the
Okay.
options.
No, I'm even talking about the final exams. I'm talking
Oh,
about
the
the final
exams,
exams.
I'll attach the paper with the periodic table so that you can see some of these things.
You do it over. We know our people. It will come and it will not be there. You will do it too, but our people it will come.
She bought it. She brought the periodic table.
Yeah, nuclear.
Oh yes,
Mr. Yusuf,
that's what he did.
This is Mr. Yusuf, I think this is clear. Please, since if and only you are the one who is said the question, you just bring it, the mass number and the atomic number, so that we'll be free thinking of the periodic table and what have you. Because once you get to know the atomic number and the mass number, then definitely we are true to go. Once you bring the symbol, we are pleading that you once you bring the symbol, don't leave the atomic number. Once you bring the mass number, add the atomic number too, so that to make things easier for us. Other than that,
I get the point you are coming from. But then if you bring everything to in that manner, then it means you are going very low to the SHS level, because those are the people that you have to bring all the, like you indicate the mass number and the atomic number for them to just do it straightforward. At the higher level, you just write this and it's assumed in, they have to know. And I don't want to reach you, but that's why I want to attach it for it to be easier for you. So that if anyone does the question paper, they'll know that, oh, okay, this is an advanced level, not the SHS level, because the question has to be standard. So that when you go out there, they'll know that, oh, okay, this is SHS level or something.
Okay, so
can we go with our own periodic table?
Yes, you can, but then they sell no foreign material. So if it's attached to this, yes. So what I will do is, even though I will attach the question and the periodic table to the question paper, but if you are having something you can take it along, so that
they will not allow us, please.
That's what so that you don't take it in there, you keep it maybe in your bag or something at the examination center. So when they bring it and they say you are not seeing it there, you can ask them that you need a periodic table. So whatever be the case, you just tell them you brought yours. You just go and take it and use it.
Yeah, I think that is also a good idea.
Yeah. For me, I will attach it. Okay. I will attach it, but then I don't know how they are going to do it, because when the papers are sent to them, they have a way of doing their own thing. So
okay.
So you can take one there to the center in case if they don't give you the access to the timetable, the periodic table, then you just stick to yours. You tell them and you use your own.
As for the invigilators in Zenit, this one day it shouldn't be possible for them. Once you are going into your bag, you are going for a pop. It shouldn't make sense.
I think sometimes when we talk to them about it, some of them will agree, because if they see that it's just a periodic table that nothing is on it, I think
some of them don't know what is a periodic table. So it is, you are the only person.
Yes, I do understand. Some of them are not science students, but then say Munyaman can you have to come together and let them know that this is the situation. And then in that case, they will understand, because it's not just one person complaining, but Munyaman can get it. But if they will not really mind you guys.
There's sometimes when this is not given, the constants are not given. I tell them, and sometimes someone will search on the net. If the time is taking too long, someone will search on the net for it, then they'll just give it to us. So it's like you have to talk to them and let them understand that you need it. But for me, they have to understand that it's supposed to be given, but it's not given. So then you have to help us out. If the time is far going and you are still waiting for the lecturer to give it out, and the lecturer hasn't given it out yet, do you want me to wait? No, then you just search.
And But I
It's not like I am teaching. It's something that's supposed to be there.
Okay, so
Now, Madam
like
Felicia,
we said,
please hold on. Madam Felicia, who name UCC Center?
We all witness
me
something.
The bill or Kaswa,
We all witness something.
the
Now,
only physics student in Kaswa.
you decide
Kaswa there.
Kaso yɛn
Kaswa,
wɔ hɔ. Me nkoa na meyɛ science physics wɔ hɔ.
no, Kaswa, I'm a land of possibilities. It's with the session in some way.
Kaso no sɛ wontumi ntwa wo ko.
Don't worry, it shall be all right.
Land of wonders. Land of wonders.
And one I can't. You know, some copper periodic table back a marking scheme. I'm there, but that's why.
But sɛ you see, I think normally I hear code phone ka ɔmo joining yɛn na nkɔmɔ ne yɛ learn lectures. Nti I think that yɛ agitating kɔmbɛte na nkɔmɔ etimi ayɛ wei. But I can normally see recording only, but previously no ɔmo ankasa joining personally.
Oh, sir, they will not join. No, they just record. They join to record. They join to record it. But they don't actually sit in the class. No.
Previously, when we started with semester 1, they normally join for some times and then they will leave.
Oh yes, that is just to see that the lecturer is actually in class and teaching. That is all.
But nowadays they've not been doing like what we have been saying. They have to hear us and then also make their homework.
Hey, they are here. Oh, they are here. Deborah is here.
So she has to identify what we are saying, put them down, and then let. Okay, let's.
Madam Fisher, we have been complaining since the commencement of this month, and nothing has been done. No need to complain again. You should leave them
because they will not mind us.
Hello, can you see?
Yes,
please. Let's continue. Let's continue.
So we move on. Yes, please.
Yeah, now we have seen that some centers are ahead of other centers. Our center like this, Zenith can be compared to a typical village center. If you have the opportunity of checking online to get a constant, obviously you do better than people in Zenith. So then I think that when such a thing happens, then they are not being fair. So sir, please do something about it. Because if you are the one marking, you should observe those trends. That then this is what happened, and that is why other centers will perform better than other centers. Thank you.
Oh, with that one there.
Yes, what I mean is that our own, we don't get the center, we don't get the constant. No, I'm not saying
what you are saying, but that one is not necessarily for us to consider some points and some stations to other stations. It has to be uniform, so that if I'm going to consider some centers, then it means at the end of the day, when you are dashing mass across board, should I exempt them?
No.
It means that they are getting 100%. We are getting
25%. Please. The thing is that don't take it as if like it is something that is being done. Like I should say, just say it and it is done. I can't remember from our center at first they won't even mind us. Even across the biology and the chemistry people, they won't mind us.
What I mean is that you have a listening.
We talk with them that sometimes that these things is supposed to be provided, but it's not provided. So the first thing they will do is that they'll contact the supervisor, the chief examiner, the
coordinator,
the chief the coordinator there. Then the coordinator then will also the one at the stage the center will then contact the main coordinator. If their calling is not going through, and after some time, like an hour or so, it's still not going through, then we just tell them to help us out by providing it online. Some agree,
so that's
some
what we are saying,
disagree.
that you have that opportunity. At least they are able to listen to you. But we, no matter if you like go to hell, they don't mind.
Hey,
they won't listen. That is what I'm saying. They won't listen. That is my brother. We are the same center.
Then that is not good.
They won't listen.
That is not
so
good.
Sometimes I write at the bottom of the question, constant was not provided. Constant was not provided. That's what I'm saying.
These things, one of our lecturers taught us something that if the constant is not provided, just write the symbol for the constant. then just go your way. Just write the symbol for the constant and add it to the final this thing, the final answer.
Yeah,
Then
that's true.
just go your
Sometimes
way. Because the
The man
constant is
that
supposed to
the
be
waste your
divided,
time.
but anyway.
I'm
My uncle, it's a useful to us, so
not
it's a useful to us.
Nina, Pastor Bien, so Walai, yeah, Pastor Bien,
It's true, but it's true, sir. It's true. And it's true, pa.
Let's move on. I do understand the point that Mr. George is talking about, but that one I can consider some. For example, the normal could I think in one of the exams, right? It was a practical exams, and practically it has to do with graph. And
Yeah.
I think the center was Northern Region, Kamale, what. Instead of the students requesting for a graph paper, or the graph paper, I don't know how to run a graph on the answer booklet in Walibu. I just I can't mark that thing. Yes. On one draw the Y S and Y as is on one number. In the uniform, on one I find we are draw to the point, I draw lines in the graph. And I can't mark that for the person. So some of these things, there's no consideration in that.
Yeah, I think I think that person you should give him, you should even give him extra mark, because for even wasting time to even draw the graph, to draw the graph is another issue. If you was able to draw and you got it correct, then I think you should even give him +10. We'll say.
George,
Graph now, graph sheet.
Meanwhile, the graph is there. You should ask for graph. You didn't ask for graph. You did it yourself.
He was not giving. Are you sure?
The graph is
Boss,
there.
are you sure? Are you sure you will be giving? Even SHS, you are giving graph.
Have you not been giving graph before?
No, so are you trying to tell me that if you are writing a practical exam and there's a graph and request for a graph and they are not giving the graph,
they won't give it to you.
You draw the graph in the answer booklet.
So the graph was finished, so I have no option.
That person is a genius. That person is a genius. He's very smart. Genius for that matter.
About smartness.
Smart about it. George,
let's continue. Why we are wasting our time. Let's continue.
Let's continue. We back.
So we move on to the energies of nuclear reactions. So that in the case where you have a reaction and we want to see or find the amount of energy that is produced at the end of the reaction, how do you go about with it? And as you know from the rest mass expressions, right, or from the Einstein's energy as far as a particle is concerned, which you have mass at the square of the speed of light. Okay, so in that case, you find the mass or the energy of the individual atoms present in the nucleus, in the reaction. And when you do that, you first find for the one at the left-hand side. When you are done, you do for the right-hand side. And in the case where you realize the energy at the left-hand side is not the same as the one on the right-hand side, then the excess will be the energy that was being produced. So, for example, we have this reaction. Okay. We have this reaction, which is giving us, let's say, T plus a proton. Okay. Giving us our R and our X. Okay, so this is the reactant side and this is the product side. So that at the end of the day, if you find the energy of this, you find the energy of that, you find the energy of this and the energy of that, they have to be the same. That's we are talking about the conservation of energy. So in the case where they are not the same, that's where you have the amount of energy that is being produced. And you and I also spoke about the fact that for any reaction or for any element or nuclide to undergo radioactivity, that means the number of protons and the number of neutrons are not the same. I hope you've not forgotten about that. That's where we talk about the binding energy and all those kind of things. So when you find the mass defects and you are getting negative, you should know the implications. When you find the binding energy and you get positive, you should know the implications. That of the negative, you should know the implications. Okay. So that when you put it in this way, at the end of the day, what is over here must be the same as what is over here. I hope that is clear. Please, I hope it's clear.
Can you repeat it?
Okay. Now, we are talking about the nuclear reaction, the energies of a nuclear reaction. And you said the reaction you are considering is this, that's the shorthand form. Now, if you write it in the long form, this is how it's being written. I have the T, which is serving as the parent nucleus, right? And the P, that's the proton, which is acting as the thing using to bombard the parent nucleus. Sorry, the parent nucleus. And at the end of the day, it's going to give birth to a product nucleus, which is the R, right? And now the X, which is the emitted particle or the emitted or byproduct. Okay. Now, we also know that the energy of any atom is given by, that's, let's say the energy is E, is given as mc squared, where the M is the mass of the atom you are dealing with and the c is the speed of light. Okay, so it means at the end of the day, if you have the energy of this, it's going to be m of t, that's the mass of the t atom, and the c squared, right? Then plus that of the mass of the proton here times the c squared must be the same as that of what is over here. Okay, so at the end of the day, if you find the total energy at this side, it has to be the same as the total energy at this side. I hope you are with me.
Yes, please.
And always the left hand side is the one that is using as a reference. And I'm saying the left hand side is the one using as reference because that's where the parent nucleus is, or the parent atom is. Okay, so always this is the reference. So we use this to compare this. We don't use this to compare this. So that at the end of the day, whatever you get over here, you use that one to compare this. If the one here is lesser than this, then the excess or the remaining that was in excess is the energy that was being produced. And we don't have a case where, or it's very, how should I say, it's very rare that at the end of the day, we have an energy here that is larger than that of the reactant side. Do you understand what I'm trying to say?
Yes, please.
Sir.
Yes. So always what we have over here is lesser as compared to the one at the left-hand side. And when you do that, the excess that we have is what we are telling as the energy that was being produced at the end of the reaction. And because always the energy that we are looking for, that's why we bombard them with all these things so that we get excess energy. And that excess energy is what we use in generating electricity, those kind of anything that we want to derive from this kind of products. I hope you are good.
Yes.
With that, when you want to find the binding energy or the kill energy, which we have already spoke about, it's just going to give us this way, of which I know you know. So that if you take all the ones here and you subtract all the ones over here, the excess that you are getting is the energy that was being produced, the excess energy that is being produced that you are looking for. I mean, this expression, we've already spoke about this, so I know you understand it. Right? And I want to say something.
Yes, sir. No.
Okay. So that is it, because you just factorize the c squared out. So you just substitute the mass of the reactant, then you subtract the mass of the to that side, and at the end of the day, what you get to be the excess mass, and then the excess mass and the C square will give you the energy that we are talking about. Okay. So that is also that, and that's all what this session is also talking about. And go to interaction of heavy and light charged particles with matter. And this is where ideally it's just talking about how gamma rays and those beta things are being produced, because you realize when we have heavy metals or heavy atoms and want to split it, splitting them is where we are talking about nuclear fission. That's we are breaking down into its simpler forms, and in the case of breaking them apart, we are going to produce energy, and these energies are what we are using, or we are talking about in terms of the nuclear fission and nuclear fusion. Okay, but then you also have to talk about the one that have charges. Okay, in the case where you break them down and you are going to get ions, and that's where you can also talk about photoelectric effects, because you know in photoelectric effects, this one the photon hits the target metal surface, and then an ion is being produced or an electron is being ejected. Okay, so in that point you are talking about those kind of photoelectric effects and the Compton effect. But when we are talking about without no charges, then we are talking about the nuclear fusion and nuclear fission. And that's all what the interaction of heavy and light charged particles with matters are concerned about. Now let's look at the interaction of heavy charged particles with matter. That's the energy loss mechanisms. So one, Coulombic interactions between the particle and the electrons in the medium is the basic mechanism for the slowing down of a moving charged particle in a material medium. And this is common to all charged particles. And point two, I think I'll leave this point for you guys to read about it. It's not anything serious. So you move to the interactions of photons with matter. Interaction of photons with matter. And when you are talking about photons, we are just talking about light energy. Okay. So when light energy interacts with matter, what are some of the things that happen? Or what are some of the things that you should pay attention to? So interaction of photons with matter by which individual photons are removed or deflected from a primary beam of S or gamma radiation may be classified according to, so one, the kind of targets. So what is the target? Are we using electrons to hit the matter? Are we using an atom or a nuclide to hit the matter? Or what type of photon are we interacting with? Okay, so those are the things that you have to pay attention to. One, what are you using as the target? The mechanism to hit the target nucleus. Is it an electron? Is it an atom or a nuclide? What kind of photon are we dealing with? And two, what type of event are you talking about? Are you talking about a scattering event? Are you talking about absorption event? Or we are talking about pair production or pair annihilation events? I hope I'm not confusing you guys.
No, please.
No.
Okay. So those are the two things you have to pay attention to. So if you know that the target atom is the thing we are using to hit the parent nucleus is an electron, then you should know at the end of the day what you are looking for. And if then what you are using to hit the target is an electron, at the end of the day, what kind of reaction are you talking about? Then it means you are talking about the electron capture. I hope you remember that.
Yes, sir.
Yes, sir.
Okay. And when it's an atom or a nucleus or a nuclei, what are you talking about? I mean, that one you can talk about either a negatron reaction or a positron reaction, or can also talk of which they are all the beta interactions.
Sir, please, the previous page, there's an equation there. Or it's
Which
not that.
This one.
Yeah.
Oh, don't really stress yourself about this. But then it's talk about the power or the energy when you are talking about reactions, because you can find the energy, and if you can find the energy, means you can find the power, right? Because power is ideally work over time, right? Now, when you are talking about in terms of distance, then you can just find its energy respect to the distance that it has traveled. Okay, and when you are doing that, you are finding the power. And these are all constants that you will be given. All the constant that you should know when you are treating some of these things. For example, if you want to find the stopping power for, let's say, a helium atom. Now, for helium atom, you know the mass, right? And the V, you know, is constant. That's the velocity, which gives you the speed of light. And the Z, we talk about the atomic number, you have to know. And the N is the neutron, the Z and the P all will be constant that you should know. So that you just substitute them in, you can find the stopping power. But then I don't want you to stress yourself about some of these things. That's why I didn't really mention it. But then it's something you should read on. The fact that I skipped doesn't mean that you shouldn't read. At least read it for your better understanding. I hope it's clear.
Yes, sir. Thank you.
All right. Then we go to the type of interaction that take place, okay, with atomic electrons. And some of them are one, the photoelectric effects, the Rayleigh scattering, the Compton scattering, and the two Compton scattering, that's multiphoton effects. So we are talking about, so we are looking at I, we are looking at this one, okay. And now we are talking about what if the target is an electron. If it's an electron, what are some of the interactions that we get? And that is one, we can get photoelectric effects, because you know when we are doing that and the electron is being ejected, and we are talking about photoelectric effects. You can also talk of Rayleigh scattering. And you can also talk of Compton scattering, which Compton and Rayleigh are kind of the same, just that the photon or the electron ejected and the photon that is being absorbed is what it differentiates the two. Because I know for Rayleigh scattering, at the end of the day, all the photon is being absorbed and the electron is ejected. By the Compton scattering, the photon releases the electron, then the energy of the photon reduces, gets smaller, but at the end of the day, you still have a photon that is also being produced as a byproduct, and also the electron. So that are the two differences. And can also talk about the two photon Compton scattering, where I don't know, they have all the two, that's the Rayleigh and the Compton, all being effects. Okay. And number two, the interaction which occur with nucleons. Then you can talk of the photonuclear reactions and the photofission, which is also absorption. You can talk of elastic nuclear scattering, that is the gamma-gamma. And you can also talk of inelastic nuclear scattering, which is also the same as the gamma-gamma. Okay. Then you can also talk about the interactions with electric fields surrounding charged particles. Interaction with electric fields surrounding charged particles. I can talk of the electron-positron pair production, and also the electron-positron pair production in the electron field. So the first one is in the field of nucleus, and the second one is the field of electron. Can also talk about the nucleon anti-nucleon pair production. And can also talk about the interactions which occur in mesons, which is the photomeson production, and also the modified gamma-gamma scattering. Okay. But out of all these processes, the main ones that we always talk about, or the main five, is just this one. Okay, or the main ones that we really consider as far as photon interactions are concerned is just this five. And that's why when you were treating with modern atomic physics, these were only the four that we spoke about. Not that All these ones are also not interested. They are also interested, but then that's an upper level sample. So that if you want to specialize in some of these things, that's where you go into detail to find out the things that's also okay. But as far as this course is concerned and to this level, these are the 5 that we always really pay attention to. And this one, even the first 3 is where most often our attention is being based on. That's the photoelectric effect, content capturing, and pair production. The photoelectric effect, content capturing, and the pair production. Okay. Then we can move on to, so for example, you see what we have over here. They say complete the nuclear reactions, and they're giving you this. At the end of the day, they're expecting you to know that's the daughter nucleus that is being produced. And knowing the daughter nucleus, they're expecting you to know the mass number and the atomic number as well. So if you're not having the periodic table, it will be difficult for you to know the kind of product you are being getting, unless you just write the mass number only and you eliminate the atomic number. By doing that, you know the exact daughter nucleus that you are being produced. Okay, and that's why I said when we do that, I'll provide you the periodic table that will guide you in knowing the exact thing that is being produced. I hope you are good.
Yes, sir.
Yeah, so with some of these examples, I think you can just solve it whilst you are home. Because with that one, you have your phone, you can look for the both the atomic number and the mass number and solve them out and the product that they will be producing and all that. Okay. So you see a question 5 like this. It says state 3 types of interaction if that occurs between photons and electrons. So when you talk of electrons, what are some of the things that are being produced? Photons, electron production. That's why you can talk the photoelectric effects, the Compton effect, and the Rayleigh scattering. I hope you've done all that. That's what you're having over here. That's all what this is talking about. Okay. Okay, so I hope it's not going to be an easy, very difficult. So if actually it's an electron with a photon, then these are them. If actually it's a neutron with a photon, these are them. And they are all over here. So if you are asked to state the 3 types of interaction, if that occurs between photons and electrons, photons and neutrons, and photons and mesons, it wouldn't be any issue. Okay. Then we move on to the nuclear cross section. Nuclear cross section. Nuclear cross section. Okay, so the probability of a nucleus reacting with a neutron is described by a physical quantity called the cross section. The cross section may also be understood as the effective cross-sectional area of a nucleus seen by a beam of particles. So if you have a radiating object or a radiating atom, okay, and you're able to find the cross-sectional area of that radiating atom, then we are talking about the cross-section. And the cross-section area also talks about how intense or how energetic this can cause. Let me see how intense this radiation will be and the impact it will have on you. Because assuming if the cross-sectional area is small, the impact, though you still have the effect, but the rate at which it will have effect on you will not be as the one compared to the one of a very high cross-sectional area. Okay. So that's all what the cross-section also talks about. So I won't really spend. So if you look at what you have over here, with this beam, this is the cross-sectional area we are talking about. So assuming we have, let's take this.
Hello, sir.
Yes.
Please, can you come again with the cross section?
I said with the cross section, right? So let me use this to explain for you to get it. Assuming we have an atom, right? Or we have a radiating particle. Now, the cross-sectional area of the radiating particle is what you are talking about, the cross-section. So, for example, assuming if this radiating particle is having a cross-sectional area of this circle. So, this circle is what you are talking about, the cross-section. And I was saying the cross-section also tells us, or it gives an idea about how intense or the effect of the radiating particle on an object. Okay, so for example, if you have this area that has been radiating on the surface of a human body, and you take that one as the square, at the moment the impact or the harm the square will cause will be very much higher as compared to that of the smaller one. If I'm talking about the impact, I'm talking about respect to damaging the tissues. But because, as we said, when you are talking about this kind of radiation, we always take our attention to the highest energy ones. That's the gamma and the X-rays. Okay, and the gamma, as we said, it cause DNA, can cause DNA structure or change in the strands of the DNA. Okay, so with that one, it even kills. Let me put it in that way. If you've watched the documentary about the Fukushima and Chernobyl events, you could see those who were having a very high cross section. It can kill you instantly, but the one that the cross section is very small or doesn't really take the whole body, the person will be able to evacuate, but then it will take some time before the person dies. Okay, so the cross section have an impact on how the energy is going to impact on you, and that's all what the cross section talks about. Yeah, Mr. Mark.
Okay, thank you, sir. So, sir, if I understand you well, here the cross section is the area that is exposed to the ray that is coming in contact with the body. So, like you were saying, okay, so like you were saying, like the Hiroshima and Chernobyl disaster, those whose entire body was exposed to the radiation, they died. But if maybe small part of your body is now exposed, then maybe even if you die, it will take some time. So the cross-sectional area here is the area that is exposed to the radiation.
Yes, but then most of it, not necessarily the surface that is exposed. It's talking about the beam that is coming. Okay, so the area of the beam. And you all know this is the divergence anyway, no.
Yes, sir.
So you see, this radiation is bad and it's being divergent. So you take the divergence theory into as it's coming, then it's diverging, and as it's also diverging, the energy is reducing. Okay, so the closer you are, the smaller the cross-sectional area, but the higher the energy or the intensity that will be absorbed. But the further you are, the wider the cross-sectional area, but the lesser the energy. Okay, so at any point, what is the area of that beam? I hope you understand what I'm trying to say.
Yes, sir. Yes, sir.
Yes, so that is all what the cross-section is talking about. Any other question?
Hello, sir.
Yes, please.
So please, I want to understand it clearly. Is the cross section or the cross sectional area, is it a property of the nucleus or the projectile or both?
It's not a property of the nucleus. The nucleus does not have any property as a cross section. It's like let me bring this in our everyday activity. Assuming say what's our flashlight, right? What's our torchlight? You see, say the closer you are to the torchlight, the brighter it is for you, right? And the smaller the area that light is bright. But air quality won't say after that brightness in a but then I enlarge the scope now air brighten. Okay, the more now air travel further and further now area na yekese, but area na yekese now the brightness is so coffin. So the only property of the atom or the nucleus you are talking about here is the energy level. Okay, the energy level is what is the property of the atom, but then as it travels further, that one is as a result of the divergence theory. So as it's covering a whole wider area, then the energy is becoming lesser.
All right, sir. Thank you.
All right. Any other question? Okay. So that is also about this, and these are all what it tells us about the area and the kind of impact it will have on the body. That's if the area is small, what is the impact? If the area is wider, what is the impact? And these are all some of the calculations in there. And with this, I know we've done this. With this, I know we've done this. And that's where we find the power that we have the energy as a result of the distance. That's the one that I think Mr. George was asking about, that equation. Yes, you see, we know that as usual, if we want to find the power has to do with time. But with this, we said we are doing it with respect to the distance that we are away from that. Okay, and we have, I think we've done this up there. Okay, because we know power is respect to the energy over time is what we term as power. But this time around, we don't really want to pay attention to the time, but we want to pay attention to how far you are from the radiating particle. That's why the power is with respect to the distance. And that's why when you come here, the area is also with respect to the x, so that the further you are from the radiating particle, that's where you know the area, the cross section that is being exposed. And if you know the cross section that is being exposed, it can also give you an idea of the energy level that is being impacted at that point. Okay, so this is all calculation or some derivation that you need to, it's talking about it over here, of which I won't really spend much time on it. Okay, then we move on to please don't really spend my time on this point. So move on to nuclear fission. Nuclear fission, and with the whole nuclear and particle physics course, this is one of the topics that you should pay attention to. That's the nuclear fission and the nuclear fusion, and that's where all the mechanisms are. That's all where the mechanisms are. It will be all your course. If at the end you are not able to explain this well, it means course now and one in the year. Okay. So nuclear fission, in your own words, a cast of fission, how do you understand it?
That's putting things together.
Fission.
Please, it is splitting of
Splitting, basically.
a heavy nuclei or perinuclei in this daughter nuclei.
Yes, that's correct. So it's what you said is fusion. This is fission. So fission means trying to break things into smaller particles. Okay. Fission means breaking something into smaller particles. So if you say nuclear fission, is a splitting of a heavy nuclei into smaller, splitting of a heavy nucleus into smaller nuclei. Okay, into basically, let's say there were a boba just one quantity, right? Now you have one more, let's say 5 and now 4, then means you are doing what? A fission reaction. So if you have something like uranium, now uranium, it's neutron linear to daughter nuclei of that uranium, it means at the end of the day, you are doing a fission reaction. Okay. And that's what nuclear fission talks about. So nuclei with atomic numbers greater than 83 are unstable, although some have very long half-lives. So they are saying any nuclei with atomic number which is greater than 83 are unstable, although some have very long half-lives. Above this value of Z, that's above this value of, that's above any number above this 83, the repulsive electric force between the proton is greater than the attractive strong nuclear force between the neutrons, and the nuclei disintegrates. That's the nuclei undergo radiation. For most naturally occurring nuclei, the decay is by either spontaneous alpha or beta decay, and these are often accompanied by gamma decay. However, there are other possibilities. And what are some of the possibilities? So in some cases, a very heavy parent nucleus decays into 2 medium mass, that's daughter nuclei. So most cases, we have only one parent, right? And they undergo just 2 daughter nuclei. So the ones that are very common is that they split into just 2. Just 2. And this is called nuclear fission. And the material containing nuclei that undergo fission is said to be a fissile material. So any material that can undergo a fission reaction is said to be a fissile material. Okay. Please don't forget this statement. If you are asked to find a fissile material, what does it mean? So any atom that undergo or that can undergo a fission reaction is said to be a fissile material. Okay.
Objective question.
Also objective question.
People are settling their questions. People are settling their questions.
We have crashing. Yeah. Thus, nuclear fission is a process in which heavy nuclei, that's where the atomic number is greater than or equal to 230, split into 2 lighter nuclei due to the electrostatic repulsive between numerous protons. This also involves the release of 2 or 3 neutrons. For example, plutonium is formed from the uranium isotope via neutron capture followed by 2 beta minus decay. So with uranium, undergo neutron capture, meaning you use neutron to hit the uranium. Please, I hope you understand, because when we were talking about the beta reaction, we said you have electron capture, and the electron capture, what it does is the electron is used to hit the parent nuclei. Likewise, if you talk about neutron capture, we mean the neutron is used to hit the parent nuclei. Okay.
Hello, sir.
Yeah, hello.
Yeah, sir. From the fissile material, you said that nuclear fission is a process in which heavy nuclei. So the A there, you said is atomic number. I think it's mass number. As to confuse some people.
Oh, sorry. Then thank you. The atomic number rather, when it's greater than or equal to 230.
No, sir. Like it's mass number.
There is mass number and there is the atomic number.
Yes, but you said atomic, so that's why I want to draw your attention.
Oh, okay. Thank you for that. So yes, I think hand is up. Is there any question, Mr. Samuel?
Yes, sir. When we're doing nuclear and environmental physics, we came across all these things, the complicated equations, like plutonium splitting, giving you 3 neutrons, and a positron or whatever. One that came in the examination, that the equation alone was 1 page. Just the equation for that chain reaction was 1 page.
That was the
So,
case news.
and the case is yes. Okay, I don't know if this course will get there, but what I want to know is like, can we be memorizing these kind of things? Like, this will decay and give you 3 neutrons and a positron, and or maybe in examination you provide us with the equation and we will have to maybe answer questions on them. That is my
Oh
question. I really have
no.
to.
The thing is, I'll give you maybe the parent nuclei, and I'll tell you it's undergoing a fission reaction. And with the fission reaction, let's say this is the product, right? So I won't tell you all the products. Maybe I'll give you the daughter nuclei that you need. That will guide you for you to know the number of neutrons or whatever that is being produced as the byproduct. So you have to be able to tell me that, oh, okay, then this will be the reaction. So let me, for example, if you see this one, right? He said the uranium is used to produce plutonium. So we give you the uranium here and we give you the plutonium here. Okay, that this is the product and this is the reactant and this is the product. Okay, and we tell that it's undergoing a neutron capture. So I'll give you this, right? And I'll give you the final one to be the Pu. Then I'll just add the mass number and the atomic number there for you. So in order for you to tell me the reaction, you have to know that, oh, okay, then I don't know, they have to balance the reaction. Now, balancing the reaction, how is it going to be like? So that you now go back to the conservation of the mass number and the conservation of the atomic number. That if this is neutron, this is the uranium, this is 1 0. So 1 0, this plus this, what gives this here? Then 1 plus this, what am I getting over here? So that the excess that is not here, it will give you an idea of what is being produced over here. I hope you understand what I'm trying to say. So let me just write something here so that at least in the question, I can say, let's say we have 2, 3, 8, and we have 92, and I have U, right? And in bracket, I have neutron capture, comma, gamma radiation as a photon that is being produced. And I have 2, 3, 9. Then I have 9, 4. And I have Pu. Okay. Now, if I give you this, this reaction is not balanced, right? So in order for you to make sure it's balanced, that's what the work you have to do for me. Please, are you with me?
Yes, sir.
Yes, please.
So that at the end of the day, when you add the neutron, which you know is 1, 0, when you add this and this, now this goes to 29. So 29 at the left-hand side, we have it to be 29. So the mass number is conserved. Now let's go to the atomic number. Now this is 92, this is 0. Now this is 94. It means this has SS2. And how come that is being done? And that should tell you that then you have to get 2 neutrons over there. That will balance the whole thing for you to get the same thing that is over here. So in order for you to know that, that's the whole work you have to do for me. I hope it's clear, Mr. Samuel.
Yes, sir. So like if I get you, because sometimes like you may tell us that this one is decaying, but then we may, in trying to identify the products, we may just make a mistake or skip one or forget that maybe there are 3 neutrons instead of 2, or maybe there is a neutrino or this or that. That is my problem. Sometimes we
Oh,
may
with the
just
neutrino and the other aspects, you don't worry. My interest is balance the whole thing. That is it. My interest is
okay.
balance it. So that at the end of the day, if I look at the reactant side and the conservation of the atomic number and the mass number, or the conservation of the neutrons is observed, I'll give you your full marks.
Okay, sir.
So in this case, you see they even brought gamma radiation here or a photon over here. In your case, you can choose to eliminate the photon. I don't have any issue with you. But my issue is, if you're eliminating the photon, then put in there what is over there that is balancing the equation. So that if you put in the n over here, which is 2, that's you have 2, then into brackets your n, which is 1 and 0. Then it will make me believe that you know what you are doing. So that at the end of the day, when you do that, you have 2, and that will make everything balance over here. Simple. I hope it's clear.
Yes, sir.
Okay, yes, sir.
Okay, so that is all what I want to see, not necessarily for you to write plenty derivation. No, I don't need that. I just want to know what is needed for us to balance it. Okay. So since the uranium produces a fissile nuclide, it is called a fertile nuclide. A fertile nuclide. Fertile nuclides can only be split by fast neutrons. To realize at first, we talk about fissile material. We're also talking about a fertile nuclide. I hope you are following.
Yes, please.
Okay.
Yes, sir.
A chain fission reaction can sustain itself only in the presence of a sufficient quantity of fissile nuclides, though a smaller or share in the process is also contributed by fission by fast neutrons on fertile nuclides. Also, natural or spontaneous fission is also common in artificial produced nuclei. For example, the fermium-256 nucleus may undergo spontaneous fission into a xenon nucleus, that's a palladium nucleus, and 4 neutrons. And likewise, the same thing. This one, you don't have any capture. This is just undergoing radioactivity, and it's giving us 3 products. That we have 2 daughter nuclei, and we have a neutron that is being released as a form of a byproduct as well. Okay. So this is example of the natural spontaneous or natural nuclear fission. So the artificial one, you realize, oh wait, you hit the parent nuclide or the target with either a neutron or whatever, so that it can split. But with the natural ones, you don't really necessarily have to hit it with anything. It's undergo radiation by itself. Of course, it's not stable. It's trying to split itself into other daughter nuclei for it to be stable. I hope it's clear.
Yes, please.
In some cases, it can be the case where I won't just write it this way for you. Maybe I'll put it in a diagram form, so that let's say I have this, okay, and let's say I call this my neutron. I have a bigger thing like this. Okay. and I say this is the parent nucleus, right? So it's plus rather, it's not this. And I say it goes in there and it gives you something like this. Okay. And maybe I'll give you the specific things over here. So assuming this, I won't say the parent, but let's say I'll say uranium. Oh no, you let me say the fermium we are having over here, right? Then I'll say now this is my XE and this is my PD. Okay. And I'll ask you to balance this for me. I hope this wouldn't be an issue. So that you know the fermium have this nucleons. Okay. And there's xenium also have these nucleons. That's of this also have these nucleons. Okay, so that when you balance this and this, it has to be the same as this. In the case where it's not being the same, then it should give you a clue about what is supposed to be here. So that then you have to tell me that then there's supposed to be an extra thing that is being produced, which is, let's say, 4 neutrons. Okay, or someone can just choose to just do one thing, and the one you just write 4, then add the end to it. So that at the end of the day, when you add this to all this here, you have to give you the sum of whatever you're having over here. I hope it's clear.
Yes, sir.
Okay, so it's not always the case that. Yes.
With the diagram, yeah. So in this case, there will be no atomic number.
There will be nothing here when you are sticking to this, because this is a natural spontaneous fission. So that one, you don't have a neutron here. But I was trying to use this for the example, so that with this is artificial. So you have to first hit it with nucleus before, sorry, neutron, before you'll be able to produce the product.
I'm even referring to the atomic number, the mass number. It will be provided.
Going to be given. I'll give it to you.
Okay.
And if not giving credit, so basically I'm finding out from the periodic table that I'll give you.
Thank you.
All right. Any other question?
Hello, sir.
Yes.
Sir, please, what would we say is the difference between a fissile material and then a fertile nucleus?
That is your work. First one, I catch a one now towards the objective question. When I'm saying defining more.
Because I was trying to establish the distinction between the two, but I was finding it a bit difficult. So if you could help me, please.
We catch on the bed exams. I send me on my exams.
Okay, then.
I think with what is in the model.
Come again,
since they say that, with what is the model, for me, I can say that the difference is how it can be split. I think this one, you say the fertile nucleus can only be split by fast neutrons. So I think that would be the difference. So it can only be split for a fertile nuclide. It can only be split by fast neutrons. By a fertile nuclide.
Are you sure?
I think.
From what you are saying, the fertile nuclide is part of the fissile nuclide.
A fissile nuclide is a new nuclide that can undergo fission reaction. And you said uranium is an example. Uranium is a typical example of a fissile nuclide.
Why? Yes.
Why? Because we can split it into or it can undergo fission reaction.
Undergo fission.
Split it into different 2 or more daughter nuclei, right? And we are also saying It's a fertile nuclide. Why is it a fertile nuclide?
I'm saying for what is written there.
Yes,
Is
so
it
it
fertile
can only be
nucleus can
split by
placed
fast
by
neutrons.
fast neutrons?
It means it can undergo fission reaction. Yes, we know. But then how does it undergo? Tell us that it's an artificial fission reaction, meaning it needs to be bombarded with something.
Okay.
Because if you look at the fermium over here, it's also a fissile nuclide. Okay. But we won't say it's a fertile nuclide. Why? Because you don't need to bombard it with anything before it's undergo fission reaction.
Okay. So one is all right. Okay.
At the end of the day, don't
Fertile
expect
is
me to say.
about
At the end of the
it
day,
being
don't expect me to say
artificial.
much on baby.
We beg. I hear. We beg. Consider the age.
So please, is it okay now?
Yes, sir. Yes, sir.
Okay. So the difference is that we just need one is artificial, and the undergo artificial fission reaction is said to be a fertile nuclide, and the one that does not undergo is just a fissile nuclide.
Okay.
Thank you, sir.
But also, when you are talking about fission reaction, at the end of the day, energy is being produced. And the energy that is being produced, so share at the end of the row here, you won't be able to see the energy that is being produced. So always, if you want to find the energy produced, you have to give you the masses, respective masses, so that if you substitute in their mass and that of the C square, you can find the energy that has been produced. I hope it's clear.
Yes, sir.
Yes, sir.
Okay. So the mass energy of any nucleus is always less than the sum of the mass energies of its constituent nucleons, and the binding energy of the nucleus is equal to this difference. As a result, fission is energetically favored and is therefore likely to occur with the consequent release of the energy difference that kill the Q value of the reaction. This energy difference is carried always as kinetic energy by the decay products. So in the case of reaction in 3.1, that's a fermium reaction, the Q value is 150 mega electron volts, and the process can be represented as this. Okay. So in the case where you find the energy at the left-hand side, then you try to find the right-hand side and balance it. The excess that we get is the energy that's being produced over here. But it's not necessary by force for us to write it in addition to the whole reaction for us to know. If the question is being asked to find the energy, you can just calculate it and leave it, tell us the energy produced. It's not necessary for us to add it to this before you get it right. When you try energy and value now, you are good to go. In some cases, a heavy nucleus becomes unstable if it captures an incident neutron or proton. If it then undergoes fission, this process is called induced fission. So they said in some cases, a heavy nucleus becomes unstable if it captures an incident neutron or proton. If it then undergoes fission, this process is called induced fission. An example of induced fission is that of the uranium. Following neutron capture, it is the consequence of an increase in the internal energy of the nucleus when it absorbs a particle, most frequently a neutron. This absorption produces an excited intermediate nucleus, and its excitation makes it oscillate and deform. If the excitation energy is large enough, the intermediate nucleus may take on a shape resembling a dumbbell. In such cases, the electric repulsive force between the two spheres forming the dumbbell may overcome nuclear attraction and the nucleus splits. This process is the basis of present energy generation from nuclear fission. Okay. Now the see work example, one nucleus is formed in the capture of neutron by this, and that's what we've already done there. Okay, so you just balance this reaction and you are good to go, and that's all what we are looking for. I hope it's not a big deal. because they said neutron capture. So if you are talking about neutron capture, it means a neutron to use to bombard the uranium here, and that's what you have over here. So that then you balance this equation, and balancing it, that's all. Are we good?
Yes, please.
Yes, sir.
Okay.
Yes, please.
All right, then we can move on. So you see, in this case, or maybe it's me, like I say, I don't know how to say.
Okay.
Yes.
Sorry for taking you back. Then I think there is a mistake in the solution. Because
Why?
if you look at the solution, they say the reaction equation is given as uranium 236 with atomic number 92 plus 1 neutron with atomic number 0 and mass number 1. And it gives uranium 236.
Oh, this is not balanced. So.
Okay. All right.
So this is just the intermediate session.
Okay.
Right? This is the intermediate session. So this go ahead to give you the subsequent one that is being produced. So this is not the final product. This is just the intermediate version. So at this point, you realize it has to be 237. So that's where it goes ahead and give you the delta this one that is being produced.
So say, please, is that what you...
But sir, in the question was 235, the uranium in the question.
Oh, okay. So it's typo error. Okay, thank you. So the first uranium should have been 235, not 236. Because if you look at what they have written down there, they say the reaction equation shows that the atomic number remains the same, 92, but the mass number increases by 1. Hence, the nucleus produces. So I think it is a typo error. Thank you.
All right, but then, as I said, this is the intermediate section. So this is also undergo a reaction. I don't know if you understand what I'm trying to say.
Yeah, I understand you.
Yes.
If you come down,
so like a decay,
so you realize the final product is what we have over here.
Yes. If you look at
yeah,
equation 3.3 confirms what you are saying.
Yes. So that in the intermediate version, this is also unstable atom.
Yes.
This is also unstable. Because you realize you said when the mass number is always greater than, I think, is it 230? It's undergo nuclear fission. And now you're having 236, which also tells us that this atom you're having here is also unstable. Okay, and I don't really, these are the daughter nucleus that are being produced. I hope it's clear.
Hello,
yes,
sir.
yes, sir. Yes, sir.
Okay. But some cases, or what I know sometimes you'll be confused is if you don't give you the type of daughter nuclei that you want, how will you find out that these are the products that you are going to get? I hope that's what you guys are thinking.
Yes.
Exactly.
Yes, sir. That was a question that I kept asking because, for instance, if you just say uranium is captured by, a neutron is captured by uranium, is it that there's only one possible outcome or there are other possible outcomes? And which one are you supposed to provide?
There are other possible outcomes. That's why I said, in that case, I'll give you the reactants and I'll give you the daughter nuclei that I'm expecting. So yours is to balance it and find out that, oh, okay, at the end of the day, this has to come in there. I hope you understand. So that if I give you this, okay, I'll tell you that this
it will indicate to this or that.
This and this are the guys produced. So in order for you to balance it, you have to know that, okay, if this and this are produced, when you add this and this, is it the same as what you're having here? If it's not the same, then you have to make sure that then this is the thing that you need to add it, and that is all that we need.
Okay.
Yes. So don't really worry yourself about the product that you produce, but then or the daughter nuclei will always be given. but your duty is just to balance it and know what is being produced, or the excess particle that is being produced after the daughter nuclide. Okay. The probability that a neutron will capture, is there any question?
No, sir.
Okay. The probability that a neutron will be captured by a uranium nucleus and hence that fission will take place depends critically upon the energy of the incident neutron. So as they said, if this will undergo a fission reaction, depends on the energy of the neutron that is used to bombard the parent nuclide. Most neutrons which collide with the uranium nucleus simply scatter elastically from the nucleus without any reaction taking place. The probability of capture is much higher for a very low energy neutron than for a high energy neutron. For instance, the probability that fission will be induced by a 0.04 electron-volt neutron is about 600 times larger than that of a 1 mega electron-volt neutron. Under otherwise identical circumstances, neutrons with energies of order of 0.04 electron volts are known as thermal neutrons. And if you say thermal neutrons, they really don't have a much impact on the uranium. It doesn't really undergo any reaction, but rather the uranium just sees at heat. It sees that, yes, let me say as heat. Okay, or temperature difference, instead of it to for example, let me put this way. You know, when you are talking about radiation, you are talking about energy of a photon. Okay. And this kind of gamma rays that we are saying, or the gamma radiation, are very energetic, we all know it can cause harm to the body. But then I say you feel say like it have this kind of temperature that it gives, right? Let me put it that way. It's kind of heat. If you take a normal fire, what they show I know you know the intensity. Likewise, the same as that of gamma radiation or irradiation. Okay. Even though it show, but if you are talking about the gamma radiation, it's not just burning you, but rather it's also causing harm in your DNA as compared to that of just normal fire. Okay, so if you are talking about this uranium thing, the neutrons with energy that is less than, or that is of the energy order of 0.04 electron volts. And when it is a normal it doesn't really have impact on it. But the one that is higher than that, which is around 1 mega electron volts, and when you see it, but then it's also able to cause the fission reaction for it to occur. I don't know if you understand what I'm saying.
I get it.
Yes, so the one with the order 0.04, it sees it as just a thermal or as something like heat, but it doesn't really cause it for it to undergo nuclear fission reaction. But the one which is more than that of the 1 mega electron volts, that is the one that can go further for it to cause that of the fission reaction to take place.
So like the first one, it's not high enough to cause a nuclear fission to take place. Is that right?
Yes.
Okay. So it won't be able to really cause it to do anything.
No,
unless it reaches that threshold, then that means that it can be affected by that 1 mega electron volt.
Yes, before it can undergo this reaction, the fission reaction.
Okay.
Okay. So that is that, and we have some work examples also here. Write the equation of the reaction when a nucleus of uranium absorbs a neutron, splitting into. So you see, is it giving you the daughter nuclide that is being produced? They are saying it's undergo what? A neutron capture. that it absorbs a neutron. So this is used to hit this. Okay, so when it hit this, these are the product that is being produced. So that when you have okay, the equation is even here. So that when you have the uranium plus the neutron, you should know that this is just the intermediate. Sometimes we grab a crime farmer and you don't really care about the intermediate. What we care about is it. So that at the end of the day, you have to know that if these are the products, then you balance it. After balancing it, the essence that will be given is what you are our interest in. So that this is what is going to fetch you the marks, or that's what is going to let us understand that you know what you are doing. I hope it's clear.
Yes, sir.
Okay.
Today there are no no question for further research. No
Ah,
examples for further research.
yo. In fission, a heavy nucleus placed into two medium heavy nuclei called fission fragments and a few neutrons. So in this case, this and this are said to be fission fragments. Fission fragments, which is also the same as the daughter nuclei. Apart from this, each fission also gives some gamma rays. Yes, as you said, they also produce some gamma rays, which is also the same as the energy, because gamma rays has no, they don't have any charges, or they don't have any atomic number or mass numbers. So they are just raw energy that is being produced. Nuclei can split in hundreds of different ways. Example of one with the positive fission is this. So this was the one I was trying to say. So that if we use this to hit this, I don't know, this place into this. Okay. And this is the exact thing that they are having over here. So if you look at this is the uranium you are having over here. And the neutron is what you are having here. So that when it hits this, we have the intermediate version, that is this. Okay. The intermediate version is this one. And this is used to split to the KR, which we have over here, and the BA, which is also having here. And then we have three neutrons that is being produced as SS. Okay. So you have one here. I think they eliminate the other one. They have to also be another one. Okay. Because I know that we have three neutrons that is being produced. And they also produce heat. And this heat is the gamma radiation that we are talking about. Okay, so this doesn't have any charge. They are just a form of energy. Okay. Energy, which is in the form of a photon. Photon or gamma ray. Okay. And in case if you want to find the energy of this, I hope you know that. Yes, so I want to talk about that. So as I said, in some cases too, the question can be in this way, so that I have this, then maybe I'll split this to this and this for you, and you are asked, balance the reaction. Okay. So that you have to know that if that's the case, maybe I know I'm from neutron anymore, but you have to know that, okay, if I add this and this, then means at the end of the day, I have to have 3 neutrons that will add to it for us to get the equation balanced. Okay. I hope it's clear.
Yes, sir.
Okay. But then I think, I don't know. Let's solve this question before we move ahead. Because I have a feeling something must be wrong. Now we have 236, and we have this as 92. Now let's come to this side. 56 plus 36 will give us what?
92.
It means the atomic number is conserved. Now let's come to the mass number. 141 plus 92 will give us what?
3 and 3 and 233.
233. Okay.
Yes.
Now 233, what's supposed to be added to this for us to get 236?
That would be 3.
That would be 3, right? It means
Yes.
our X is equal to 3.
Yes.
right? And we know neutron is 1
1
0.
0. Yeah.
So that if you have this plus this plus this is the same as this, right? And
Yes,
when we
sir.
have this balance, okay,
Yes, sir.
okay. Because this one, they emitted the 1 neutron, so I wanted to confirm. That's why I wanted us to solve it and balance it. Okay. Now, to sum up, fission produces fission fragments, also prompt neutrons and prompt gamma rays, and the release of large amounts of energy, which is distributed as kinetic energy among the above listed products of fission. So these are the things that are being produced at the end of a fission reaction. So we have fission fragments, which is also the same as the daughter nuclei, and the prompt neutrons. And the prompt neutrons are the excess neutrons that is being used to balance it, and the prompt gamma rays, that are these ones that we also have there. And also we have some kinetic energy that is being produced, and that is what in some cases they write the value over there. So example, this one is one of the kinetic energy that is being produced. So those are the things that are being produced, or that are the the products of a fission reaction. I hope you are good.
Yes, sir.
Okay. Then go to energy and nuclear fission. The energy released when a single heavy nucleus undergoes fission is typically 100 to 200 mega electron. So when you are talking about a nuclear fission, the energy that is really released is in the ranges of 100 to 200 mega electrons, which is about 100 times greater than the energy released when a nucleus undergo an alpha decay, and millions of times greater than the energy released per atom in a chemical reaction, such as a burning of fossil fuels. So if we burn fossil fuels, right, the energy that we get is very low as compared to the energy that is being produced when an atom is undergoing a nuclear fission. And they are saying the energy is millions times or millions greater than that of the energy produced in a burning of fossil fuels. I don't know if you understand that statement.
Yeah,
Yes.
like the bombs and this thing, the energy release when a bomb undergoes a designated is a bit high, much more higher than when you are burning a fossil fuel like kerosene or petrol, diesel, or something of that sort.
Yes. So you realize when it comes to, let's say, Ghana, right, our energy, and if I say energy, I mean the electricity. We have some that depends on these fossil fuels. That's a 2 out for gas plant. I don't know. I think you have some a triable gas plant, right? And what they do is they just use these fossil fuels because all those methane gas and all those things are termed as fossil fuels. They generate electricity from this. And they are saying when you get uranium, the kind of energy that we'll be getting from a triable will be million times greater than that. Which means if you're able to utilize nuclear fission reaction in here, the energy that will be supplied or the energy that we will get will be able to supply, let's say, the entire Africa. Because even if the small we are getting from this is able to, we are able to share with our neighbor countries, and we are come to get million times greater than that, you should know the extent it can go. Okay. So that's why if you go to the developed countries, for example, Japan, China, Russia, and those countries, they solely depend on nuclear fission or the nuclear energy sources, because the energy they get is much higher. Just that when we get an accident or those kind of things, it's very dangerous. But then if you talk about the energy that is being released, it's very, very high. Okay. This large energy release is the main advantage of nuclear power. Yes, that's the main advantage. Other advantages include the fact that the process does not consume valuable fossil fuels and does not produce greenhouse gases. So when you are using fossil fuels, they also don't have any environmental effects. As much as the safety precautions are being obeyed and there's no incident or accident, is a clean energy. Okay, the environmental impact only comes, or the negative aspect only comes in when you are having accidents and those kind of things. All current nuclear reactors are uranium as 4. Use uranium as 4, yes, because uranium is the one that undergo artificial. The common one that can undergo artificial reaction, and if it undergo artificial reaction, means then you can stop it, because immediately you stop feeding it with a neutron, it means you are trying to stop the reaction. Okay, so that's why uranium is the one that is mostly, or the current one that is being used. So for example, if I'm producing heat using uranium, it's just a matter of continuous, spontaneous emission of neutron for it to be able to bombard the neutron, then the energy is being produced. So if I want to stop, I just stop feeding the uranium with neutron, and then the energy starts reducing, and that will be all. I hope it's clear. Okay, so natural uranium has a composition of 0.72 this and that of 99.28 out of the this. So the uranium isotope, when we are undergoing fission reaction, the uranium-236 or the 235 gives a percentage of this, whereas the uranium-238 gives the energy of this. Okay, so you know the kind of energy that you are being produced when you are using the uranium atom or the isotope. It is the uranium-235 that is the desired isotope, as it readily captures thermal neutrons and undergoes fission. The isotope 23892 makes little contribution to the fission process. As a consequence of this, modern reactors use enriched uranium phosphoride, which have a uranium-235 content of about 2% and 3%. The fact that each fission induced by a single neutron gives rise to several more neutrons in the fission processes. It brings with it possibility of a self-sustaining nuclear chain reaction. Yes, so as we saw from the previous reaction over here, that's when this reaction is undergoing or is taking place, always we have neutrons that is being captured as some of the byproducts. But I also know that the neutron is what is going to supply the uranium to also undergo another fission reaction. So if you have a reactor like this and you are using this, there's no need for you to supply many neutrons. But the byproduct is also supplying neutrons, which in turn, if you subtract you subject this to also another uranium isotope, it means it can also undergo reaction. So for example, as much as we are producing this, we can also introduce another uranium-235 here. Okay. So that some of the neutrons over here can also react with it and also give us another energy. Okay, so in as much as we are getting more energy here, there's no need for you to supply the thing extra energy. So if you want to just stop it, one, you seize this one, and seizing this, you also find a way of extracting the neutron that is being produced over here. And how do you do that? That's where you can talk of the negatron and the positron reactions. That if you want, you have neutrons and you want to seize the neutrons, what do you have to do? What atom do you have to introduce so that the neutron will just cease producing? I hope you get my
Yes, please.
okay. So that is that. And this is the reaction that we are talking about. So for example, we have the uranium here, we supply it neutrons. This breaks down into two, but this is also accompanied by another neutron. So that if that neutron, this hit this one, this hit this one, we get this, right? And this also undergoes spontaneous reaction. So that the nucleus that this one is also produced, we hit this with that, we hit that with that, also produce another one. And the reaction continues in that form. Okay. So the uranium you get even a very small amount is enough to produce very large energy for a very long time. I hope you get it. And with this, we have a name for calling each of the stages. Okay. So if you look at this, the first one that is being produced is called the first generation. Why? Because that's the immediate energy that is being produced from the parent daughter. And the second generation is the energy that is produced from the daughter product that was produced. The third generation is the other one that was produced. So it takes on in that order. You have fourth generation and all that. So if you want to find, or if a question is given and they ask you what is the fifth generation of neutrons, or the fifth generation as far as maybe a certain uranium chain reaction is taking place, you have to tell us that, oh, okay, so the fifth generation stands for the product that is being achieved under the fifth daughter nucleus in the chain reaction of a uranium atom. I hope you get it.
So, sir, can you say that the fifth generation is the fifth chain of reaction that occurs from the parent nucleus?
Yes, you can say that. That is accepted.
Okay.
Yes. So that is that. Then go to difficulties in chain reaction. One, what are some of the difficulties? So absorption of neutron by this, the major part in natural uranium is the isotope 238, which has 99.3%. The isotope U235 is very little, which is 0.7%. It is found that 238 is a fissionable and fast neutrons, whereas 235 is fissionable with slow neutrons. Due to the large percentage of that of 238, there is more possibility of collision of neutrons with 235. It is found that the neutrons get slowed on colliding with 235 as a result of its further fission to 238. It's not possible because they are slow and they are absorbed by the 238. This stops the chain reaction. So as they are saying, when you are dealing with the 235, which is normally used, right? Or the 238, which produce a very large energy. Okay, that one is kind of seen as a natural spontaneous or natural fission. But the 235, the one we bombard with a neutron. Okay, but then they are saying when you bombard it, always the neutrons, the reaction come to a stop. Why? Because when the neutron is being absorbed, because we have the 235 and the 238, the same reaction. The 238 is having more. Please, a minute.
Okay, sir.
Hello, sir.
He says a minute.
And I wanted to ask you if you can take that 10 minutes break. The things he was going to do, sir.
Are you going to wash?
Today, the judge is not watching. I think that today the judge won't watch. Right now, then you have to go and eat. Judge will eat, not wash.
Yeah. Hello.
I'm saying,
Yes.
please, my people were saying that I think we should take the 10 minutes break.
Oh, okay. I
Since you
wanted
were
us
doing
to
something.
I wanted us to finish this so that when we come back, we just go to the nuclear reaction. But then,
Okay, okay, then let's do that. Let's do that.
a dozen maybe.
Hey.
So let's go for the break and come.
Okay, that's it. Thank you very much.
You're welcome.
Oh.
Hello.
Hi, sir.
Can we start?
Yes.
Some 10 minutes. My mom 20 minutes.
Achepa started.
Yo. Okay. So moving on. As we said, when you are talking about nuclear reaction, the fission reaction, one of the difficulties we face is the nuclear or the chain reaction comes to a stop because of the capture of the neutron of the uranium-235. Now, how do we solve that? To solve that, you have to sustain the chain reaction of the 235 is separated from the ordinary uranium. So at the end of the day, you need to separate the uranium-235 from the 238 so that the 238 will not capture the neutron, but hence lead to spontaneous production of the uranium-235, then the excess neutron that was produced in the reaction. And uranium, so that uranium so obtained in the 235 is known as the enriched uranium, which is the fissionable with the fast and slow neutrons, and hence chain reaction can be sustained. And what is the other issue that we also get? Other one is also that if neutrons are slowed down by any method to the energy to an energy of about 0.3 electron volts, then the probability of their absorption by uranium-238 becomes very low, while the probability of other fission of this becomes very high. And that's why we said always we use energy which is around 1 mega electron volts. Because if you use one which is less than that, it is always captured. That's why we said it's known as the thermal neutron. It is captured by the 235, and the absorption becomes very low. But then if it's above 1, that's 1 mega electron volts. In that case, please hold on. Yeah. Oh, sorry. Yes. So when the energy is around above 1 mega electron volts, that's where it's being captured by the uranium-235, and that's what helps in the chain reaction production of the algorithm of the fission reaction to occur. This job is done by moderators, and the moderators are okay. We go there in the nuclear reaction. You have what you call moderators, and these moderators are the ones that stimulate the reaction. Okay, and the moderators that also helps if you want to stop the reaction to take place. If you want to induce or reduce the neutron in the reaction, the moderators are the ones that helps in doing that things. Which reduce the speed of the neutron rapidly, graphite and heavy water are the example of moderators. So example of the materials that they use in these moderators are either graphite or the heavy water, which helps in reducing this reaction. And I hope If you say heavy water, do you understand it?
No, sir.
No, please.
Okay. Don't expect me to tell you. You will see it in your quiz. So I'll bring a statement and I'll ask you what that is. So go and know what heavy water is. And as I said, if you see heavy water, they said it's used to stop. It's an example of moderator, and it's used to stop the chain reaction. Okay, it blocks or it reduces the neutrons that are being produced in the chain reaction. So at least it should give you a fair idea what heavy water is. And also have the critical size. So the neutrons emitted during fission are very fast and they travel a large distance before being slowed down. If the size of the fissionable material is small, the neutrons emitted will escape the fissionable material before they are slowed down, and chain reaction cannot be sustained. And how do you solve that? The size of the fissionable material should be larger than a critical size. So if you are talking about a fissionable material, the size of that one should be large as compared to that of the critical size. The chain reaction once started will remain steady as a rate or retard depending upon a factor called the nuclear production factor. And then the nuclear production factor is as the ratio of the rate of production of neutrons to the rate of loss of neutrons. Okay. So the production factor just talks about the proportion of the neutrons produced to the proportion of the neutron lost in the reactor or in the nuclear reaction. Now, if K is equal to 1, the chain reaction will be steady. So it means if the rate of which the neutrons are produced is the same as the rate of which the neutrons are lost, it means the reaction will be steady, the chain reaction. But if the reaction, the reproduction factor is greater than 1, then the chain reaction accelerates. It means the chain reaction will be increasing as time goes on. It means the energy produced will be much higher, as in, I don't know how to put this. So example, assuming if let me put this in a normal day activity. We have some kind of investments, and I say yes, let me say investment that we discuss Kushima in the normal sense. To say the invest this car in normal sense, let's say you buy shares at any bank or something. If you invest a normal shares, normal the rate at which maybe every month, also 9 every year also. But then when you talk about where the reproduction factor is high, in the normal month, if I say also half of your money, no. This time around in a month, they'll give, let's say, times 3 of what you are getting. You need to get in a year. And
GKM.
Which one is that one?
Men's good.
Men's good.
Yeah, so in that case, you realize the energy that is being produced is in excess. And in that case, it's very critical. It's very critical. In the case of nuclear energy generation, that's where you need to bring in the moderators so that they will slow it down. In a case where we don't use the moderators in that thing, that is the idea they use in creating these nuclear weapons. Okay, because the nuclear weapons say sure, and I said if it explodes, assuming the neutron generation, and let's say the reaction to let's say 1:1. But in this case, because the reaction is increasing, the reproduction per constant is higher. Okay, the reproduction factor is higher. If the acceleration in the 1:1, goes and now let's say 1:20. So at any given time, the thing is just multiplying. And that's why if a nuclear weapon is being dropped, it covers a very wide range, and its impact is very strong, and it covers a very wide area because the reproduction factor is very high as compared to that of a normal one that we use in our energy generation. That's in the case of nuclear reactors. And if the reproduction factor is less than 1, then the chain reaction gradually comes to a halt. So if say the rate of which the product of neutrons are produced is to that of the loss of the neutrons is less than 1. Once as time goes on, the neutrons will be finishing. And as the neutron finishes, it means the reaction will stop. Why? Because the neutron that is used to bombard the uranium for it to undergo another chain reaction. But this time around, instead of saying a neutron is so thick. So neutron is so thin, that means gradually there will be no neutron in the system that will bombard with the nuclear, the fissile nuclide for the chain reaction to continue. I hope it's clear.
Yes, sir.
Okay. So the main tool that we pay attention to when you are using it in energy generation, that's in whether electricity generation or whatever, is the first one and the last one. Okay. Now the second one is where they use in making weapons. This one they just use in making deadly weapons. That are some of the bomb and those materials. But with this one, the nuclear reaction, that's what we do. Okay, they make sure that the production rate and the loss rate is the same. So that nuclear reaction, energy they produce are constant and steady. So that at any time you say, oh, this is the amount of energy that is being produced, and this is the amount that will be generated at any given time. Okay. And now, assume you said maybe the energy in the system, I know, yeah, point number 1. And assume you said, they say also, oh, energy now, it's normal, it's okay. What do you do? Then they now reduce the K value. Okay, so that the K value will be less than 1. And when it's less than that, it means now they are reducing the neutrons in the system. And as the neutron is reducing, then the reaction is gradually coming to an end. In case maybe one person will general maintenance or something, or maybe there is a fault or an accident in that case, and they want to pay attention to, they just make sure that the reproduction factor is less than 1, so that gradually energy they producing now is so better for a certain time, and the thing will come to they do what. Yes.
Yes, there's a service mark. Yeah. Please, so anytime you want to stress, I've noticed you have been using the account language, the tree language. We from Voter also part of. So if you come here blending the AV2, we'll be happy.
Oh, okay.
Anytime you want to stress a point, you have to.
sorry.
So we Voter, we are also part.
Okay, sorry about that though.
No, that's okay. I and then the Benedicta, we are from Vuta. We are only 2, and that's center there.
Okay.
Okay. That's by the way, anyway.
All right.
Thank you.
You're always welcome.
Yeah.
So that is that. Then we go on to the types of chain reaction that we have. We have the controlled chain reaction and the uncontrolled chain reaction. And the controlled chain reaction, that is the one that we use in our energy production. Because if you have a reaction that we can't control, at the end of the day, if there is an accident, it means we can't control it. It will take over all the place. But if you have a case where you have a control over that, okay, and on the control is where always you have the K to be equal to 1. Because when it's equal to 1, it means we are trying to make sure that always the energy produced at any point is constant and steady. So that when we want to reduce the energy, we just make sure that we substitute it with some energy or some atoms that will absorb all the neutrons in the system, and the K will be less than 1, so that at the end of the day we can bring everything to halt. So in the chain, in the types, we have the control and the uncontrolled one. So the control one is always by artificial method. It's always by artificial method. An example is the uranium, that you have to supply it with nucleus, and then the whole system starts. By the uncontrolled one, no control by this type of nuclear reaction means we can't control this reaction. So example of this one too is the one we saw earlier on. Is it the radium atom? We said that one is natural, and you know something natural. There's no way to stop it. Okay, just that we have to have a way of, maybe if it's harmful, we have to have a way of blocking it, or the method of saving it. Okay, the reservation, and that's why when we come here, we don't really have to deal with those uranium and other stuffs. Okay, because I think uranium, Zambia, either Zambia or some country like that is now mining uranium. And I think even Burkina, they do some. And the thing is, if they mine it, because they don't have storage facility, it becomes an issue. And that's why these France people and all those people just can't mine and take it away. Because if they get it, storage will become an issue. Also, they don't have the nuclear plants for them to use. Okay, so in that case, you don't even have to bother yourself by mining, because if you mine it and you can't control the reaction, at the end of the day, you are going to harm your citizens. So the uncontrolled one is always the kind of natural radioactive or the natural fissile materials or fissile nuclei. Also, with the control one, all nutrients are absorbed except one. Yeah. So when we talk about the control one, we make sure that all the neutrons in the system, we have moderators that absorb these neutrons, leaving just one. And that is the one that will always be used in doing the spontaneous chain reaction. Okay, because you realize, for example, the uranium one you saw over there, at the end of the day, you have 3 neutrons that is being produced. And if you have 3 neutrons there, it means when you subtract them, we subject it to another uranium, you're going to get multiple times of energy that was being produced at the first reaction, which is going to be in excess, which we can't even control it. But then if we have moderators, and these moderators are to absorb this uranium and the neutrons in there, leaving just one, it means we can know the chain of the energy that has been produced, or we can monitor the energy. We will know that it will be steady, because at any point, we are just using just one neutron. So at any point, you know the energy that is being produced. But in the case of an uncontrolled one, always the neutron that are being produced are more than one, and hence always the energy are in multiple. You can't really detect the energy in the system at any point, unless you know the generation you are talking about. So that if you know that, oh, okay, I'm in the 4th generation, then you have to multiply the energy produced at the 3rd generation by a multiple of 4 before you know the generation of the amount of energy that is being produced. But if you don't know the generation you are, it means you can't really know the amount of energy produced there. But with the controlled one, because you know the amount of energy produced at the initial point, you should know that it's the same energy that is produced at any point in generation. Because at any point, we have only just one neutron in there that is making the reaction to take place. And the third one, we can say the control chain reaction is also, the rate is also slow. It's also slow. As we said, we use slow moving neutrons. As compared to the uncontrolled one, we use a fast moving neutron. So the rate of which the reaction takes place is very fast. And also the production factor in the control one is always equal to 1. But the uncontrolled one, the production factor is always greater than 1. And that's where the energy is very high, you can't even control it. And that's sort of, and energy liberated in this type of reaction is always less than explosive energy. So the control one, always the energy that is being produced is less than the one that will cause this kind of harmful impacts or explosive, or the accident that will occur is not that harmful as compared to the uncontrolled one. Because at that point, you know the amount of energy produced. So if you know that, assuming I'm using a reactor, right, and I know in the reactor it's a control one, so at any point, the energy I'm getting is 200 mega electron volt. It means it's a controlled one. At any time, if something is to happen, I know the amount of energy is there, so I know how to shield my environment. But if you are using a controlled one, the amount in there is so huge that when it explodes, you don't know the amount of energy uh, that have been contained in the reactor or in the process. So in the case of trying to evacuate or find a system to block this energy produced is very difficult. Okay. And also when we talk about the chain reaction is the principle of nuclear reactors. Yes. So in the chain reaction, we always use that in the nuclear reactors to just generate either energy or for study for academic purposes. I want to go to the uncontrolled one. That is the principle of making a bomb. That's atomic bomb, nuclear weapons. And that's why when they do this kind of weapons, hardly would they test it. I don't know if you've heard that maybe some country have made a nuclear weapon, let's say atomic bomb, and they are going to test it before. And majority of these countries that say they've made atomic weapons, no. Probability that maybe the thing doesn't even work, right? They don't know. Just that they use the principles in doing it and they've been able to design it. But because they've not tested it, it becomes difficult for you to know that it really works. And if it really works, they also don't have an estimated amount of energy that will be produced. Though it's a theoretical calculation that they've done to know that, okay, if we do theoretically, this is the amount of energy that is being produced, and this is the cross section that will be affected by that. But then in practical life, they've not done it because they don't have that kind of environment or a place to test it to confirm with the theoretical mindset or the theoretical analysis they had. And that's
Yes,
why.
to add to what you are saying, in 1960s, France tested one in Algeria. By then, they colonized Algeria, so they tested it over there. But that one, they did it in abandoned mining pits, deep down. That is where they tested it, and up to now, they say that the environment is not good for growing plant and other stuffs. So, like you are saying, they don't have a place to test it. Mostly, in the previous years, what they do is that they test it in the sea, and people fought against that they are harming the sea animals and stuff. So, yes, now they can't test it anywhere.
Yeah. So now you see countries saying they have nuclear weapons, but then all they know is theoretically they follow what documents say, and that helps them in building them. But practically, they do not even try it to know whether it works or not. So that's the idea. Because I think Russia has the vast land as far as Earth is concerned. Russia is the one having the very gas. I don't know if it should, because now the world map coming out is that Africa is the largest.
The biggest, you said.
You said?
It's still the biggest.
In terms of country is still the biggest. If continent, yes. And in terms of countryside, it's still the biggest.
Yes, I'm talking about countryside. In terms of country, Russia is the largest landscape,
landmark. Yes.
Landmark, yes. And within this landmark, about I think 1/3 or so is not it's 1/3
habitable.
It's not habitable. And this is due to the fact that there was an explosion which has to do with nuclear things, and because of that, it's been years, but still the land is not still habitable. You get it? So these things is quite dicey when they are doing it. So they just do practical aspect and theoretical aspect. The practical aspect always becomes an issue. To see how wise, you guys can also try and do something and tell the world that also have a nuclear weapon. They will fear you. Just for them to come and know that it's just knockout. So you can do something.
That is why they are beating Iran left and right to prevent them from getting nuclear weapons. So if Ghana we try, they will kill us.
Sir,
we can do it.
We can do it. Just that we will never use if the is first, we may use it on Togo. We can do it.
We can't do it. It not in our lifetime.
Our nuclear weapons
Oh,
are
boss, we can do it. And we have Ghana Atomic Energy Commission. If we are giving,
that energy
if we want to
commission was
rebel, we
established
can do it. We are
to
just that. No, boss,
electricity.
just that we are
And even
following
that one, you have
international.
not been able to do it.
I think
Ghana Atomic Energy Commission. They are producing electricity from it. If you don't know, they are producing electricity from it. So we can do it. Just that.
I think
just that. The reason is that
the last time I went to Ghana Atomic Energy, I think that was 2018 or so. When I went there, the question I asked them was, are they able to produce nuclear weapons? Because if you have a center which has to do with atomic stuff, then you have nuclear reactors for scientific or academic purpose, then you should be able to do those things. And it seems they don't want to disclose it. So I believe they have nuclear weapons, just that the cross-section at which it has impact is very small. That's what I think. I think it's not powerful as compared to the other countries have.
Sir.
Yeah. Yes.
Yes. Why are we interested in the negative aspect of this energy? We should have also asked them whether they are able to do that to solve our energy crisis.
Oh, I also asked them.
Yes.
The thing they were saying is they are training people because as it stands, our fear is in the negative aspect if there's an accident. Yes, that is the fear. So they were still training people to be able to have a way of controlling some of these things when some of these incidents are to happen.
Oh, okay.
Also brought idea.
But has it been long that you went there? Has it been very long?
2018. That is 2018.
Yeah, because now, the last time I checked, they are producing electricity, but just that is what they use to power their place and then the neighboring community. So they are producing electricity from it. That is
yes,
the last time
by now they should do just that. They've not come to the production of which it can serve the whole country. And
sir, now the biggest generator of electricity by using nuclear energy in the world is France. But they are saying that even the cost involved in generating electricity by nuclear is even higher than the electricity that you generate. So now France itself is moving away from nuclear generation of electricity to other green forms like wind and photo.
They are not telling us the whole.
What I learned is that
what
I know is
if they are not telling us the truth, maybe it's true. But that is what they are saying.
So it's how to deposit the byproduct. It's how to the byproduct that is produced. To deposit is very dangerous. Whatever you produce out of it will still be radioactive, so it can pollute the environment. So last time, if you go to places like Japan and the rest, they have a very big hole that they are storing the heavy water that was accessed. They are storing it in terms of, so they will store it, not that they even go under the sea and drop it there. So it's not after the production, it can produce far greater amount than what you are producing. Just that each byproduct is dangerous.
So George,
each byproduct is very dangerous. Yeah.
So George, like you are saying, if the byproduct, the cost of maintaining it is very huge. So effectively, you see that what you generate from it is I mean, the cost involved in generating it is much more than what you get. That's what I'm saying. Like you are saying, Japan.
Okay, I get you.
Yeah, like Japan that you are saying, they have a lot of nuclear water that they don't know how to dispose them. It is costing them money. They don't know. Just recently, they said they wanted to release it into their waters. And people were saying that is not good for them. So that is what I'm saying, that the cost involved, you see. So even France, they are now saying that they are moving away from using nuclear to generate electricity to other forms like green
And
I
and
guess.
and
I guess.
uh-huh.
So in effect, you are saying it is not safe.
Oh, for safe, it's safe. Very, very safe. It's
Mhm.
just that the byproduct, as he said, the byproduct is also um, dangerous. Okay.
So
But
the whole
most
process is
cases,
not safe. That's what I mean to say.
in most cases, they
Mhm.
release the byproduct in the sea. Mr. Samuel,
Mhm.
you can please stop.
Yes, sir. I wanted to come here. I think that we are saying certain things that are actually factually incorrect. So we need to correct certain things. Um, I've been following this nuclear thing a lot because of what is happening in the United States, where now the whole world they wanted to go to green and they want to go solar, wind, thermal, and so on and so forth.
Yeah, like
And
the renewable
since
energy.
Trump came in, he has now gone, on this nuclear revolution where he now. What was actually happening in the nuclear thing is that you see, nuclear technology is very old, and so we always think about Chernobyl because Chernobyl there was that explosion and it rendered that part of Russia uninhabitable for so many years. Now, nuclear power has improved so much that now that problem is no longer an issue. If you go to China, I think China are building like 50 nuclear plants every week or so. That is what now Trump wants to do in the United States. And it is far, 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 far cheaper. So what my brother is saying that those in France realize that it is more expensive. I don't know where he's getting that information from. And in terms of the waste, the nuclear reaction produces like a bucket full of waste because the uranium is just a rod, and that rod will produce just a tiny bit, or after the decay, it's a very tiny thing that is buried deep underground. When it's buried deep underground, it will continue to decay naturally for so many years. It will never come to the surface, and it doesn't mix with the water because when the nuclear reaction produces the energy, it is the energy that heats the water, so the water doesn't contain any radioactive stuff. So the water can be, and the water is used to drive the turbines. So the water too has no radioactive waste at all. So it is very, very, very safe. And especially the ones that are being produced now, there is no issue at all. It is far better than the wind and the water and those things because the wind is so ineffective. Solar too is so ineffective. And the solar, you think you are talking about solar panels. All these solar panels are produced in China using steel and using the traditional methods of producing the which produces CO2. So what is going on is that now the Western world they want to go back to the nuclear and stop all this wind solar thing that they were champion. If you go to the UK has the highest energy bill in the whole world. Energy is so expensive over there is because they are using the wind and the solar so much. But now that the US are going back to nuclear, it is really saving them. That is what I wanted to say.
Oh, okay. With the case of France, I was thinking because France was getting their uranium from Burkina and they are now cutting ties with them. That's where they are not getting it. And they are giving out those excuses. Okay. But what I know is the water that the waters are the water that we are talking about here is the heavy water. The heavy water that we use as moderators. Those are the ones that we are talking about the story. But what I know is most often these waters are channeled to the sea. They are always channeled to the sea. And that's where I think when we went to Gaya Summer 2018, I even asked them when they were talking about that. I asked them then why can't they channel it to the sea so that then we know if there is any waste product that's being produced can be channeled to a point where we don't have any much distance to it. And they said they were thinking about it. But as I said, it's been a while I went there, so I didn't know what they were doing for all this while. But since they are doing it, it means they can still go ahead and produce this a lot of energy that they you need to sustain the country. Just that we are humans. An accident can happen. We don't, in as much as safety precautions are there, anything can also happen. So that's it. But then it's one of the let me say the cheapest energy, because a very small amount of uranium we get can use to a very whole lot of energy for a very long time. Just that the risk that is also radioactive is somehow
safety issues.
yes. As
Okay.
I said, it's not that harmful. Then I think we don't have an issue as far as this is. Then we go on to application of fission reaction. That's the nuclear reactor, and this is where we used in producing the electricity we are talking about. So a nuclear reactor is a device in which nuclear fission can be carried out through a sustained and controlled chain reaction. It is also called an atomic power. It is thus a source of controlled energy which is utilized for many useful purposes. So they are saying that when we are talking about the nuclear reactor, it's a controlled nuclear reaction. So this is it. This is the nuclear reactor, and these are the components, okay? And these are the uranium in the fuel. And we have the moderator, okay, in here. So these moderators are the ones that absorbs the multiple neutrons that are being produced. But then, as I said, this, as the reaction goes on, the energy that is produced is a form of heat. And the heat is what is used to turn the turbines on. So this heat needs to also be cooled a little, so that in the form of controlling the amount of neutrons that is being produced, you can also control or cool the system a little better. Okay, a little bit, so that the energy will not exceed its limits. Since you are we are talking about the control one. And then we have a case. And the case is what we talk about, the shield. So that in case there is an accident, we know that, oh, okay, we've shielded the whole place. So it's not able to escape into the environment. Okay, and that's what we're about there. And the coolants run to a series of reactions. But then how do we make sure that the coolant over here is always cool? And that's where sometimes it passes through whether they see or whatever, so that anytime this thing is always cooling. Anytime this thing is always cooling, so that what here is cool, but when it comes here, it becomes hot, then it leaves in cool and hot again. It comes here, it cools, and the coolant also comes in and go through that cycle. I hope everyone understand the whole system, the principle behind this.
Yes, sir.
Okay, so that is that for us. And we have parts of the nuclear reactor and their uses. I hope this one, if you are being asked, it's not going to be any issue. That maybe you withdraw in the exams, maybe we give you the nuclear reactor and you're asked to label the parts and maybe states the functions of each of the parts that you will label. It's not going to be an issue, right? So basically, all what we need you to do is the fuel moderator, controller material, coolant, and let's say protective shield. What are the you just label this parts and you say their functions. That's all. And as we said, with the fissionable material, that is the fuel. Okay, then we talk about the moderator. It's used to slow down the electrons, the neutrons. Okay, and what are some of the examples? As we said, the heavy water and also the graphite. And the control material is also used to control the chain reaction. Also, the coolant used to cool the system. The protective shield is used to prevent escape of some of the radiations in case there is an accident or anything. So that is all. Then move on to some of the uses of nuclear power. And the most common one is in electrical power generation. And also we use it for scientific purposes, that to produce radioactive isotopes for their use in medical science, agriculture, and industry. Okay, and that's why I don't know if you've really studied these things. Sometimes we buy some, especially agric products, and they will say it's radiative. So make sure that when it expires, you dispose of something. I think I've seen something of that before. I don't know if you've seen something like that. Those fertilizers or something, they tell you it's radiative, radioactive product. So if it expires, make sure you dispose it well or something. And also, it's used in manufacturing of these atomic bombs and other stuff. And it's also used to produce neutron beam of high intensity, which is used in treatment of cancer and nuclear research. Okay. Then we have some questions here. It says find the number of neutrons released in the following fission reaction. So with this, you see the nature of the question. So you have to find the number of neutrons in there. And they say compute the reaction below. And now they say this and this. And I don't know, it's producing a neutron and then this. So you have to know the kind of atom or whatever is being produced. But with this, as I said, don't go and chew anything. All what you need to be the periodic table for you to provide in the exact atomic number so that you know the type of nuclide or fissionable material that is being produced. Okay. And they said distinguish between fissile and fertile materials. Questions now because me answer and they say energy release per fission of nucleus is nearly that. And I think this is in the slides. I don't know if I'm mentioning it. The energy release per fission of a nuclear radius is nearly what? And it's nearly 200 megaelectron because we said the energy produces in the range of 100 to 200. But the nuclear uranium atom is approximately 180 megaelectron volts. Okay. So this objective question is make sure you also solve it so that it shouldn't be like no that. Okay. Then we move on to the nuclear fusion. The nuclear fusion. What time, Ben?
11 o'clock.
Hey. And I have to move faster because you have to finish this topic. Then move on to nuclear fusion. Now, nuclear fusion is the opposite of nuclear fission. So with this one, we have radioactive materials, right? That are smaller ones. Then we put them together. Smaller ones that are unstable, we put it that way. So you can have, let's say, 2 or 3 unstable nuclei. And because they are all not stable, we put all together and they form just one atom, and that atom is more stable. Whenever you talk of that, then you are talking about nuclear fusion. And that is all this section also talk about. It's when a heavy nucleus undergoes fusion, and fission energy releases because there is a net loss of energy and mass energy and has increased in kinetic energy. This is equivalent to saying that there is a net increase in the average binding energy per nucleon. So it seems that the nuclear mass numbers is between 30 to 80 are more stable nuclei. Whenever a more stable configuration can be achieved, nucleons will try to achieve that configuration. Let me just get to this point. Nuclear fusion is a special nuclear reaction, opposite of fission. Like all nuclear reactions, the reactants are converted to different elements. That's fusion. Reaction occurs when nuclei of a which is less than or equal to 15 combine to form heavier nuclei. In other way, heavy nuclei, that is nuclei with atomic number which is greater than or equal to 180, break up into nuclei of smaller mass number. So you see the changes between them. With the nuclear fission, we said always it should be greater than or equal to 80. But in fission, it has to be less than or equal to 15. So the smaller one comes together to form a big one. But with the fission, it's the bigger one that separates two smaller ones. Okay. The most familiar and promising nuclear fusion is the conversion of a deuterium and a tritium into a helium with the release of a neutron and a lot of energy. There are many more possibilities and examples of difference in mass resulting in the release of tremendous amounts of energy. And the one we are talking about is having the deuterium atom, which are this. This is one, and this is one. Okay. So these two are said to be unstable. Okay, and when you want it to be stable, it just fuse and we have just one deuterium, we have hydrogen atom, and we also have a proton, and we have edge of this, which is also released. So at the end of the day, it goes into another reaction again, and the product we get will be a helium atom, just one product over here. Then a release of an energy which is equivalent to 24 mega electron volts. I hope you are clear.
Yes, sir.
Okay. Now each nucleus, let me skip this, we are fast behind time. Now let's look at the example we have here. One note, then I think, let's go on. 1 gram of hydrogen is converted to 0.993 grams of helium in a thermonuclear reaction, determine the energy release. So the energy release, you just have to find the mass, the mass defect. Okay, so that if you subtract this from the hydrogen, get the mass defect that was being produced. And then when you multiply this by the C squared, which is, I think, in mega electron volts, you know that one. You multiply it by the mass, you should get the energy that is being produced. I hope you are good.
Yes, sir.
Okay. Is there any hand up? Okay. So now we have some atomic rest masses of the lightest isotopes. So we have hydrogen, neutron, deuterium, tritium, helium. That's the helium-3 and the helium-4, and their rest masses that they have been produced. So that if in case we want to find the energy they are being produced as far as they are undergoing fusion reaction, you can easily go ahead and estimate the energy produced. For example, if you say this is going to give us a certain atom, it's just a matter of adding these two, you find out the product. And when you get the product, you then have to trace it to the energy at the energy produced to see if the conservation of energy is obeyed. Okay. So these are some of the basic ones that at least you should have idea of. That doesn't mean you should go and chew anything. Now you are adults, you don't chew, you understand. So we move on to, these are all readings which I'll leave for you. And yes, when we were talking about nuclear reaction, he said the reactor, or where the nuclear reactions, the reaction takes place is the nuclear reactor, or is the fission reaction. Now when you come here, how we the fission that undergo this is said to be thermonuclear reaction. A thermonuclear reaction. Okay. Please, you need to read through because we are fast behind time. That's why I'm trying to skip some of these things for us to go to the common ones that's, or the main things. When is this internet? Okay. So we have more of the reactions, and some are what we are seeing over here. And you know, in each nuclear fusion reaction, you can see we have gamma radiation being produced. Okay, so realize the first one you have gamma, second we have gamma, third we have gamma, and the last one we have gamma. Which means in any nuclear fusion, you have a photon. a photon or a gamma radiation that is being produced at the end of the reaction. Okay. Now the binding energy per nucleon of deuterium and helium is this 1.1 mega electron volt and 7 mega electron volt respectively. If two deuterium nuclei react to form a single helium nucleus, what's the energy released? So it's a matter of just this because twice of this is used to produce this. Okay. But mind you, in some cases, you realize the energy at the reactant side is not the same as the energy at the product side. Okay. Sometimes the one at the reactant is less than the one at the, it's more than the one at the product side. And that's where we take it into account for the gamma radiations that is being produced or the photon. Okay. So in a case where you balance it and realize the one at the left-hand side or the right-hand side, okay, less than this. Because for example, with this, if you are to find twice of this, it has to be more than that. In the case where you are not getting that, then you should know that the excess in it is the one that has been accounted for the gamma radiation. I hope you are good.
Yes, sir. That is the mass defect.
Yes. Yes. So if you know that, then so for example, if you look at the one this one, okay, you said two of this is used to produce this, and they give the energy for that, and have the energy for the product, okay, the fusion product. So that if you find the energy of this and this, and we subtract from this, the one that we get will be that of the let's say the mass effect or the excess energy. Okay. So if this one is giving us the helium is 7, right? And that of the deuterium is 1.1. Okay. So that if we substitute them here, at the end of the day, we should know the excess energy that was being produced. I hope you understand what I'm trying to say.
Yes, sir. Yes, sir.
Then move on to the energy from the nuclear fusion. Energy from the nuclear fusion. So in many respects, fusion offers a more attractive nuclear power source than fission. The potential advantages of fusion over fission are considerable and fairly obvious from inspection of reactions of equation 4.1 for the previous equations. These advantages also remove most of the concerns presently expressed about nuclear power. They are briefly stated as follows. So the advantage of the nuclear fusion are what are stated here. There are few problems concerning radioactive waste. So when you are talking about the fusion reaction, always when you are talking about the waste products, it's not as sweet as compared to that of the fission. Because at the end of the day, the final product we are producing is a stable atom, which is not radioactive. Because it's the reactants that are radioactive. Okay, and you are using to produce a stable atom, and that stable is not radioactive. So at the end of the day, the product of nuclear fusion is a stable atom which is not radioactive. So that's point 1. And point 2, the initial deuterium fuel is cheap and readily available. So with that one, too, when you are talking about the reactants or the fission reaction, the fission or the fissile materials, they are very cheap and they are also always available. So when you take them, it's not that expensive and you can just use it to do whatever you want. And they say seawater is a natural mixture of water and deuterium, and although the relative abundance of deuterium to hydrogen is only about 0.015%, this extraction is relatively easy and there is plenty of seawater around, enough deuterium to satisfy the present global energy requirements for billions of years. And also, there are no fuel security problems. There are no fuel security problems. That the fuel is neither hazardous nor valuable. Potential things will be well advised to take a bucket to the seaside and collect their own. Yes. So when you are talking about the fuel, for example, if you are talking about fishing, you talk about the fuel, which is the uranium 235, which is the commonly one that we are always talking about. It's very expensive. Okay, it's very expensive. So when you talk about that, you have to have a very high security. But then when you are talking about the fusion reaction, which you can use the seawater to generate your deuterium, no one will bother to come and say you have seawater there, so it's come to steal some or come to take some. Because the sea is plenty, so you can just go there and take your own. When it comes to that, the security is also not a problem as far as the nuclear fusion is concerned. Then, since the atomium is gaseous, there will be very little fuel mass in a reactor and no danger of a runaway reaction. Yes, so with the fission reaction, the runaway reaction is always dangerous, and that's where if you don't take care, you have radiation in the atmosphere, which is very harmful to the environment. But with the deuterium, it's not that harmful. So even if it's escaped into the atmosphere or in the environment, no one cares. And also, fusion is more fuel efficient than fission, producing more energy per kilogram of fuel. Fusion is more fuel efficient than fission, which produce more energy per kilogram of fuel. And then move on to difference between nuclear fusion and nuclear fission. And I'll leave that one for you to read it because I have barely some minutes to finish this. And we can also talk about or the summary of nuclear fission and nuclear fusion. So nuclear fission is used in doing the atomic bomb and all those kind of things. But the nuclear fusion is used in doing the hydrogen bomb. So you can use this as a reference to differentiate nuclear fission and nuclear fusion, where this can be the same as the fission and this is the same as the fusion. Okay, so if you want to differentiate between the two, you can just use this table to summarize it. And I think I need not to speak about it because you can just read and understand, or you want me to read? No, you can just read to understand this yourself. And you have some examples and work here you have to do. Please, you realize when it comes to the unit 3, you have plenty objective questions. Unit 2 and unit 3, you have plenty objective questions. And I'm not going to worry myself by going to take anything from anywhere. Please make sure you solve them. And if you read and you don't understand, as we said, before we start a new topic, we have about 30 minutes to discuss all these things. So if you solve it and you don't understand or you didn't get the answer, when you meet, you can just bring out your problems and we address it together. Okay. Then we move on to the section 5. We talk about photon interaction with matter. And now time is far gone. So I don't know how to do this, but then I will leave this in section 6 for you to read. Please, when you say to me read here, you just tell me so that within the week we will find extra 1 hour and do this this section 5 from what you are supposed to do. So please tell me, will you do it or I should find time and let's do it?
We will do it, but we still find time.
No, me right now, my fear or my attention is on the electric field theory because as it stands, we've done only just 1 unit, and that one is the difficult aspect. So any spare time that we get, I want us to channel an energy on that one. So
Okay.
you just let me be aware so that if even tomorrow you can just use 30 minutes to clear this before you can start with the EM.
All right. I think we read on it and then we use the 20 minutes as a brush up to it. Then we continue EFM.
Okay.
Yeah.
Okay. Then is there any question for us to address it before we call it off? Or what is in Kenya doing so?
Yeah, brush up. We just brush it up.
Castro.
Oh, but we have learned some things about this, the contents capturing and
yeah, they are the things that you did in
yeah, we know a bit about it.
physics.
That's why I said just brushing up again. Let's say about the 2 times that one.
Okay, Martin.
Yes.
On this note, is there any other question? Is there any other question?
I think no question yet.
All right. Then thank you for your time and attention. Enjoy the rest of the day.
Thank you very much, sir. All right. Have a wonderful day.
All right. And Mr. Castro,
yes,
today
sir.
nothing for you to take note of. Okay.
So my 5 months. So the 5 months that you collected, you subtracted from Castro and gave it to me. I'll be waiting for it too.
Mr. George, hold on.
All right, sir. Thank you very much.
The where's Afsan Jama? Why?
Okay, thank you, sir.
All right.
Bye.
Bye.